Imagine if there were places in space where everything we know about physics just stops making sense. Places where gravity doesn't pull you in, it pushes you away. Where mass doesn't act the way we're used to. Where something weird and unknown lurks behind the fabric of reality, breaking the rules we thought were unbreakable. Sounds like sci-fi, right? But what if I told you this is something scientists are actually considering real? What if there really are regions in space that don't just bend the rules of the universe, they flip them inside out? But before we continue, subscribe to the channel so you don't miss out on any of these videos. Now here's the wild part. We're not talking about black holes. We're not talking about dark matter either. This is something even stranger. We're talking about negative mass, a type of matter that, instead of behaving like every other thing in the universe, does the opposite. If you push it, it accelerates toward you. If it falls into a gravitational field, it rises. If this stuff exists, and there's a growing number of scientists who think it might, it could completely rewrite our understanding of how the universe works. It could explain some of the biggest mysteries in space we haven't been able to crack. And it might even tell us something shocking, that our universe has regions that are not only alien, but straight up impossible under the laws we know. Let's break this down. Because this isn't just about some weird particle. This is about the possibility that space itself, the vacuum between galaxies, the cosmic voids we thought were empty, might be hiding something way stranger than we ever expected. To understand this, we first need to talk about what mass actually is. Normally, mass is just a measure of how much stuff something has. You have mass. Planets have mass. Stars have mass. Mass is what creates gravity. The more mass something has, the stronger its gravitational pull. That's why planets stay in orbit around the sun, and moons orbit around planets. That's basic physics, and it's always made sense. But now, imagine this. What if something had negative mass? It sounds fake, right? Like, how can you have less than nothing? But mathematically, it's possible. Negative mass doesn't mean no mass. It means that mass behaves in the opposite way to what we're used to. If you apply a force to it, let's say you push it forward, it goes backward. If you try to attract it with gravity, it repels. In the weird world of physics, negative mass flips the rules. And here's the kicker. Scientists have already made tiny bits of this stuff in the lab, not the real deal, but close enough to show that the math holds up. In 2017, researchers at Washington State University created something called a negative effective mass in a Bose-Einstein condensate. That's a super cold state of matter where atoms start acting like a single quantum object. When they poked it, instead of moving in the direction of the push, the stuff moved against the push, just like negative mass is supposed to. So now the question is this: if we can sort of make this in a lab, is it possible that it naturally exists out in the universe? And that's where the mystery gets deep. Really deep. Because space is full of strange things we can't explain. Dark energy, for example. Scientists think dark energy makes up about 70% of the entire universe. And yet, we have no clue what it is. All we know is that it's pushing galaxies apart faster and faster. Not pulling, pushing. It's making the universe expand at an accelerating rate. Some scientists think dark energy might actually be negative mass in disguise. Because negative mass, by definition, would repel things. That's what we're seeing with the universe's expansion. It's like something is pushing everything apart from the inside, and that's exactly what negative mass would do. Now picture this. You're flying through the deepest parts of space. You pass through galaxies, nebulae, star clusters. And then you hit a region that seems empty. Totally black. No stars, no light, nothing. But your instruments start going crazy. Gravity is acting weird. Your ship is getting pushed, not pulled. Accelerating without any fuel. You're in a negative mass region. A place where the universe is turned on its head. These places might not be just theories. They could be real parts of space we haven't discovered yet. Or maybe we've seen them, but didn't realize what we were looking at. Cosmic voids, for example. huge regions between galaxy clusters where almost nothing exists, might actually be full of negative mass. That would explain why they're so empty. The negative mass would push normal matter away, making those areas seem completely dark and deserted. Now let's zoom out for a second. What does this mean for the universe as a whole? If negative mass is real, it could explain why the universe looks the way it does. It might even be the missing piece in the puzzle of gravity, the thing Einstein's equations need to work on the biggest scales. It could solve the mystery of why galaxies spin the way they do. Right now, we have to assume there's a bunch of invisible matter, dark matter, holding everything together. But what if it's not just dark matter? What if some of that strange motion comes from interactions with negative mass? It gets even crazier. Some physicists have proposed that negative mass could create warp bubbles, yeah, like the kind from sci-fi. In theory, if you surround a spacecraft with a bubble of negative mass, you could bend space around it. You wouldn't move the ship through space, you'd move space around the ship. That's not just fantasy, the math checks out. The problem? We need massive amounts of negative mass to make it happen. But if we could ever harvest it, faster than light travel might not be a dream anymore. And it doesn't stop there. If negative mass exists, then maybe the Big Bang wasn't a bang at all. Maybe it was a balance between positive and negative mass, a push and a pull, forever interacting, spreading space in every direction. Some models suggest that instead of the universe being created from nothing, it came from a zero-energy balance, where positive and negative mass canceled each other out, creating everything from nothing but balance. It's a mind-bending idea. But now, let's talk risk. Negative mass isn't just some cool sci-fi thing. It's dangerous. Imagine if we could get our hands on it and weaponize it. A material that accelerates in the opposite direction when pushed? That could make missiles that never stop. Shields that repel anything. Technology that breaks all our current limits. But the real danger might be cosmic. What if negative mass isn't just out there? What if it's spreading? What if regions of space filled with this stuff are slowly expanding, repelling normal matter and creating rips in the structure of the cosmos? And what if we're heading toward one? That would change everything. It would explain anomalies we see at the edge of the observable universe. It would explain why certain parts of space act like they're being shoved by something we can't see. And it would suggest that the universe isn't just expanding, it's being torn by regions of negative mass we don't understand. Still with me? Because we barely scratched the surface. This topic goes deep. Way deeper than you think. In fact, some researchers believe that negative mass could create exotic forms of matter, things we've never even imagined. Things that could make time loops, wormholes, or even alternate realities. And if those exist, maybe we're not the only ones out here. Have negative mass? How can something have less than nothing? But here's the thing, physics doesn't outright forbid it. In fact, when you run the equations of general relativity or some of the deeper models in quantum physics, negative mass isn't ruled out. It's just weird. And when something's weird in physics, it often means we're onto something important. Let's say you apply a force to an object with negative mass. Normally, when you push an object, it moves in the direction you pushed. But if the object has negative mass, it moves in the opposite direction of the force. Like you shove it forward, and it flies backward toward you. Sounds like a glitch in a video game. But it's a result of how force equals mass times acceleration. If mass is negative, acceleration flips. Now let's take that idea and scale it up. Imagine whole regions of space made of stuff like this. Not stars or planets, but giant patches of the universe where this strange form of matter is floating around. And if that sounds ridiculous, you should know that scientists at places like Washington State University have already created something similar in a lab. Not actual negative mass, but a system that acts like it. They used supercooled rubidium atoms, brought them close to absolute zero, and when disturbed, the clump of atoms didn't react like normal matter. It moved in the opposite direction of the push. Negative mass behavior, in the lab. Now, we don't know if that's exactly what's happening in space, but it opened the door. Because if we can create the behavior of negative mass in a tiny system, then it's not such a crazy leap to think that similar things could happen in the universe on much larger scales, like in cosmic voids. These are massive, empty spaces between galaxies, and we mean really empty. They make up about 80% of the volume of the universe, but they contain almost none of the galaxies. They're like the deserts of the cosmos. But what if those deserts aren't empty? What if they're filled with something we can't detect the normal way? And here's where the mystery deepens. Some researchers have suggested that these cosmic voids might be hiding negative mass regions. The reason? There are strange things happening in the large-scale structure of the universe. Galaxies moving faster than expected, the universe expanding at an accelerated rate, and we don't have a solid explanation. Dark energy has been the go-to theory, but dark energy is a placeholder. It's the name we gave to whatever is causing the universe to expand faster and faster. But what if instead of some mysterious energy spread out everywhere, it's actually that negative mass is pushing everything apart? It would explain the repulsive force. Because normal mass pulls things together, but negative mass repels. And if there's enough of it out there, maybe in vast cosmic voids, it could act like an anti-gravity field that pushes galaxies away from each other. That would make the universe's expansion not just faster, but accelerating, which is exactly what we observe. This theory is still controversial, but it's catching attention. A few theoretical physicists have started exploring models of the universe where negative mass is not only real, but necessary. And the math? It checks out. In 2018, a physicist named Jamie Farnes proposed a model where negative mass fills the gaps in space and provides an alternative explanation for both dark matter and dark energy. Two of the biggest unsolved mysteries in all of cosmology, potentially explained by one idea. That's huge. But what would it feel like to be in a negative mass region? What would it look like? We honestly don't know. If you were flying through space and entered a region filled with negative mass, would your spacecraft get pushed back? Would time behave differently? Would light bend in reverse? These are questions we don't have answers to yet, because we don't have instruments sensitive enough to detect negative mass directly. But we do see weird behavior out there, like gravitational lensing that doesn't add up, or galaxies that seem to be affected by invisible forces. Maybe negative mass is the hidden player. There's also something fascinating about how negative mass relates to black holes. You know how black holes are formed when a massive star collapses under its own gravity? Well, negative mass would behave in the exact opposite way. Instead of collapsing in, it would expand out, resisting any effort to compress it. In theory, a black hole made of negative mass couldn't exist in the way we know black holes. But get this. If a black hole made of positive mass came near a region of negative mass, the two could actually repel each other. Not attract, repel. It's like trying to mix oil and water, but on a cosmic scale. Even stranger, some theories suggest that negative mass could stabilize wormholes. Normally, a wormhole, a shortcut through space-time, would collapse instantly. But if you place negative mass at the throat of the wormhole, it could keep it open. It would literally hold space apart, acting as a bridge between 2 points in the universe. That's not just a plot from science fiction anymore. That's something real physicists are publishing papers about. And it doesn't stop there. There's even talk that negative mass could help solve the mystery of the universe's birth. The Big Bang Theory explains how the universe expanded from a hot, dense state. But it doesn't explain where it came from. Some physicists think that if negative mass existed before the Big Bang, or even as part of the early universe, it might help explain the rapid inflation that happened just fractions of a second after time began. That inflation phase is still one of the biggest unsolved puzzles in cosmology. Negative mass might be the missing piece. But here's the kicker: if negative mass exists, it means our entire understanding of the universe needs a rewrite. Newton's laws? They don't apply the same way. General relativity? It has to be modified. Even our ideas about time, causality, and motion could be totally flipped. We're talking about a concept so powerful that it might undo hundreds of years of physics, not because they were wrong, but because they were incomplete. And if you're wondering, why haven't we seen it yet? The answer is, maybe we have. Maybe we've been looking right at it, but because it doesn't interact with light or matter in a way we expect, we just didn't recognize it. That's the scary part. We could be surrounded by something truly alien, and we wouldn't even know. This opens up all kinds of questions. Could civilizations exist in negative mass regions? Would life be possible there? Could they visit us? Would we ever even know if they did? These questions sound out there, but once you allow for the possibility of negative mass, nothing is off the table. And this is just one mystery. Space is expanding, not just expanding, but accelerating. And the force causing this acceleration? We call it dark energy, but let's be honest, that's just a label we slap on something we don't understand. It's like putting a sticky note that says magic on a door you can't open. But what if dark energy isn't some mysterious force? What if it's the result of negative mass scattered across the universe? Some physicists have proposed exactly that. That negative mass regions, hidden in the cosmic voids, are pushing on the rest of the universe. Because remember, negative mass doesn't attract like normal gravity, it repels. So if enough of this stuff is out there, it could be what's driving the expansion of the universe. That means we wouldn't need dark energy to explain the acceleration. We just need a lot of negative mass hiding in the shadows of space. And here's where it gets even wilder. If negative mass is real, then it changes the rules of gravity entirely. Imagine a scenario where a regular mass, like a star, is near a region of negative mass. The negative mass repels the star, while the star attracts the negative mass. That creates a feedback loop. The star pulls the negative mass toward it, but the negative mass pushes the star away. The result? They chase each other. Like a cosmic game of tag, endlessly spinning around each other, generating motion from nothing. That breaks every rule of Newtonian physics, and yet, it's allowed by Einstein's equations. And speaking of Einstein, let's not forget that even he left room for the unknown. His equations predicted wormholes, time dilation, and gravitational waves, things that seemed crazy until we found proof. Maybe negative mass is just another part of that legacy. A piece of the puzzle we just haven't seen clearly yet. Now think about what this means for space travel. If negative mass exists, it could open up completely new kinds of propulsion. There's a theoretical engine called the Alcubierre drive that's been talked about in scientific circles. It's basically a warp drive, like in sci-fi, that contracts space in front of a ship and expands it behind, letting the ship ride a wave of warp space without technically breaking the speed of light. Sounds impossible, right? But guess what kind of material you need to make it work? That's right, negative mass. Without it, the equations don't check out. But if we could harness it, we could travel to distant stars in a matter of weeks instead of thousands of years. But here's the problem. If negative mass exists, why haven't we found it? Why don't we see it floating around, colliding with things, forming structures like normal matter? That's one of the biggest open questions. Some say negative mass, if it exists, might not clump together like regular matter. It might spread out uniformly, hiding in the fabric of space itself. It wouldn't form planets or stars, it would just sit there, invisible, untouchable, but still affecting gravity on a cosmic scale. Others argue that it might cancel itself out, existing in such a delicate balance with positive mass that we can't directly detect it. But maybe we have seen its effects, and we just didn't realize what we were looking at. Remember those unexplained gravitational anomalies? Like galaxies spinning faster than they should, without enough visible matter to account for it. We blamed that on dark matter. But maybe, just maybe, negative mass was playing a part too. Maybe both exist side by side, part of a universe that's way more complicated than we ever thought. And here's something even more mind-bending. Negative mass might mess with time. If it can bend space, it can probably bend time, too. That means you could theoretically build a loop in space-time using negative mass, and travel from one point in time to another. Time machines. Not the fantasy kind, but real, scientific models. Of course, we don't know if nature allows that. There may be rules we don't understand yet that prevent it. But the math doesn't forbid it. And in physics, when the math says something is possible, we've learned to listen. But maybe the weirdest part about all of this is that we might be living in a universe that has been shaped by negative mass from the very beginning. Some cosmologists think the Big Bang didn't just create regular matter, it might have also created negative mass in equal amounts. Like a cosmic balancing act. Matter and antimatter. Positive and negative mass. And over time, these two sides have been influencing each other across the vast emptiness of space, pulling and pushing, creating the universe we see today. So now you have to ask yourself, what else are we missing? If negative mass is real, then the map of the universe that we've been drawing is incomplete. We've been focusing on the lights, the stars, the galaxies, the nebulae. But the real secrets might be hiding in the shadows. In the voids. In the invisible fields that don't reflect light, don't form planets, but shape the motion of galaxies and stretch the fabric of space itself. And here's something you'll want to keep in the back of your mind. If regions of negative mass are out there, they might not be as quiet as we think. We always assume that cosmic voids are empty and peaceful. But what if they're not? What if they're active, full of movement and strange energy? What if they're not just regions of negative mass, but entire alien environments that operate under rules we can't even begin to understand? We're only scratching the surface. The universe is massive, complex, and more mysterious than we ever imagined. And the idea that there might be entire zones governed by negative mass behavior, well, that's not just a cool theory. That's a sign we're still just beginners at understanding the real nature of reality. Space-time without actually breaking the speed of light. It's not pure fiction, the math checks out. But here's the catch, to make it work, you need negative energy, or negative mass to hold the warp bubble open. And that's the problem. We don't have any of that. At least, not yet. But if regions of space are already made of negative mass, then maybe, just maybe, nature already has the blueprint. Maybe the universe has been showing us how to do faster than light travel this entire time, and we've just been looking in the wrong direction. Let's stop and just think about that for a second. The voids in space that we thought were empty and boring might actually be the key to understanding dark energy, solving cosmic expansion, and even unlocking interstellar travel. That flips everything. It means the emptiest parts of space are actually the most interesting. And we wouldn't have even considered it if not for this weird, rule-breaking concept of negative mass. But here's a question that hasn't been answered. Where would negative mass even come from? If it exists, why don't we see it around us? Why don't stars or planets form out of it? One theory is that negative mass might have been created during the Big Bang, just like normal matter, but was quickly repelled away from normal matter due to its strange gravitational behavior. Picture it, the instant the universe exploded into existence, matter and negative matter scattered. Regular matter clumped into galaxies, stars, and planets. Negative matter fled into the dark corners of space, pushed out by the very same laws that kept our galaxies together. Over time, it drifted into the voids, hidden in the gaps between everything we know. Invisible, undetectable, but still there. That would explain why it's so hard to find. It doesn't form stars. It doesn't shine. It doesn't gather. It avoids regular matter, actively. And because of that, our telescopes, which look for light, heat, radiation, can't see it. Negative mass might be right in front of us and we'd never know. Unless we look at what it's doing instead of what it is. And that's exactly what some researchers are doing now, trying to detect negative mass not by seeing it, but by watching how galaxies move near the voids. If galaxies near these empty regions are behaving strangely, veering off course, speeding up when they shouldn't, that might be the hidden hand of negative mass at work. But there's a twist. Some models show that if negative mass exists in large quantities, it could form negative mass galaxies. Entire clusters made of this exotic stuff. They wouldn't shine. They wouldn't emit light. They'd be completely invisible. But they'd still bend space. They'd still leave fingerprints in the form of gravitational lensing, the warping of light around massive objects. And if we start seeing lensing in places where there's no visible matter, well, that could be the smoking gun. And then there's the ultimate mystery: what happens if regular matter touches negative mass? Some theories suggest the two would annihilate each other. Not like matter and antimatter, more like mutual destruction. Total cancellation. The math behind it is messy, but if that's true, then the universe may be in a constant silent dance, keeping these two types of matter apart for survival. Or, even weirder, maybe the balance between positive and negative mass is what's keeping the universe stable. Maybe that's why the universe didn't collapse after the Big Bang. Maybe that's why it didn't fly apart too fast. Maybe it's still balanced, delicately, on the edge of these two opposites. Like a cosmic scale that never tips because the weight of positive and negative mass keeps everything in check. And if that's the case, then we're living in a universe that's not just made of stars and galaxies and atoms. We're living in a universe made of symmetry, of duality. A universe where light needs dark, gravity needs repulsion, and matter needs its negative twin to exist at all. By watching how galaxies move, how gravity bends light, and how space expands. Think about it this way: we've already been detecting invisible things in the universe for years. We don't see dark matter directly, but we know it's there because of how it holds galaxies together. We don't see black holes until they start eating stars, but their gravitational pull is unmistakable. So why should negative mass be any different? The trick is learning to read its fingerprints. The tiny anomalies in galaxy rotation curves, the strange flow of galaxies near voids, or even the unexplained dips and distortions in gravitational lensing data. Now, here's where it gets really crazy. Let's talk about the runaway motion problem. If a positive mass object and a negative mass object are placed side by side, the positive mass attracts the negative one, and the negative mass repels the positive one. This means, in theory, they'd accelerate forever. The system would spontaneously generate motion, without any external force. That sounds like a perpetual motion machine, which violates classical laws of physics, particularly the conservation of energy. But in the world of negative mass, the rules might not be as fixed as we thought. Some scientists argue that if negative mass exists, it could force us to revise one of the most sacred laws in physics. Others think the universe has a built-in mechanism to prevent runaway systems. Or maybe the conditions needed for that kind of pair to exist are so rare, we've just never encountered it. Still, the idea that a universe with negative mass could defy some of our deepest physical laws is both terrifying and exciting. And while we're talking about defying expectations, let's go back to gravitational lensing. This is where gravity bends light, and we can actually see it happening. When light from a distant galaxy passes near a massive object, like a cluster of galaxies or a black hole, it bends. And we see this bending as arcs, rings, and distortions. Astronomers use this lensing to measure invisible stuff, like dark matter. But what if the light bends the wrong way? What if instead of curving inward toward a mass, the light curves away from something? That could be the signature of negative mass. Some simulations suggest that regions filled with negative mass would create reverse lensing effects, like an anti-gravity lens. And if we ever detect a signal like that, it could be the smoking gun for negative mass in space. There's even some early data that hints at this. Certain gravitational lensing patterns don't quite match what we expect from dark matter alone. They're twisted or stretched in ways that don't make sense, unless you throw negative mass into the equation. Some astrophysicists are now going back over old data from space telescopes, reanalyzing it with negative mass models to see if anything jumps out. It's like realizing halfway through a murder mystery that the killer might have been in the room the whole time, but you were looking for the wrong clues. And if we do find solid evidence of negative mass, it's going to send shockwaves through every part of physics. It'll mean dark energy might not be an energy at all. It'll mean we don't need to invent some mysterious, invisible pressure that's stretching space. We just need to understand the stuff we've been ignoring in the empty parts of the universe. And there's one more thing we haven't talked about yet: how negative mass could mess with black holes. This is where theory gets both mind-blowing and terrifying. Black holes pull everything in, even light, But what happens if a black hole comes into contact with negative mass? Theoretically, instead of feeding the black hole, the negative mass could weaken it, drain it, shrink it. That's because the negative mass, when added to the black hole's total mass, would actually reduce the total gravitational energy. It's the opposite of how normal matter behaves. So instead of making the black hole more powerful, it makes it less. Some theories even suggest that if enough negative mass enters a black hole, it could destabilize it, potentially reversing the singularity, or even exploding it. That's a huge claim. We've never seen a black hole shrink or vanish. But if we ever did, that could be a direct hint that negative mass is real, and it's out there doing things we never thought possible. Now imagine what this means for the future of the universe. Cosmologists have always debated how the universe will end: a big crunch, a big rip, a heat death. But if negative mass exists in large amounts, it changes everything. The repulsive force from negative mass could push galaxies apart forever, more than dark energy ever could. It could mean the universe doesn't just fade away slowly, but rips itself apart violently as the repulsion grows stronger. Stars would be torn from galaxies. Planets would drift into the void. Eventually, even atoms might not be able to hold themselves together. It sounds like science fiction, but it's one of the real possibilities if negative mass plays a role in the fate of the cosmos. And that leads us to something even deeper, maybe the scariest part of all: we don't know how much of it is out there. If it's hidden in the voids, and it repels matter, then it naturally avoids every place we tend to look. It doesn't clump into galaxies, doesn't shine, doesn't gather in ways we expect. So it's possible we're surrounded by it, by huge patches of space filled with this bizarre, rule-breaking substance, and we'd have no idea unless we were looking for the right signs. That's what makes this mystery so powerful. It forces us to admit how little we actually know about the universe, about gravity, about the very fabric of space itself. Every time we've thought we had it all figured out, the cosmos throws something at us that rewrites the story. And maybe, just maybe, negative mass is the next chapter. One we're only beginning to understand. Effects, where instead of magnifying distant objects, they demagnify or spread the light out, almost like a diverging lens in optics. Imagine looking at a distant galaxy through one of these zones. Instead of appearing larger and brighter like it would through a massive galaxy cluster, it would look smaller, dimmer, and slightly distorted in a way that doesn't match anything we've seen before. If astronomers started identifying patterns like that in the cosmos, specific areas where light consistently bends away instead of toward, that might be our first real clue that negative mass regions aren't just science fiction, but part of the actual structure of our universe. Now here's another question that messes with your head: what happens if a region of negative mass collapses on itself? Does it form a black hole in reverse? A white hole? Does it rip a hole in space-time? We don't really know, but theories suggest that negative mass could lead to something called exotic matter configurations, the kind that are required to stabilize things like wormholes. In theory, wormholes, tunnels through space-time that connect distant parts of the universe, require negative energy or negative mass to stay open. Without it, they'd collapse instantly. So, if the universe contains natural pockets of negative mass, could it also contain natural wormholes? Could those voids we see between galaxy clusters be more than just emptiness? Could they be doors, not metaphorical ones, but literal structures in space, stabilized by the bizarre properties of negative mass, waiting to be understood? This is where the questions start piling up faster than the answers. Could alien civilizations, if they exist, have figured this out already? If they had access to regions of space where negative mass is abundant, maybe they aren't just using it for propulsion. Maybe they've already mapped out these exotic structures, figured out how to travel across the galaxy, or even the universe, by skipping through negative mass zones the way we might one day skip across planets. And here we are, still arguing over whether this stuff even exists. But maybe we're closer to proof than we think. In 2018, a team at the University of British Columbia proposed a model of the universe made entirely of a fluid filled with negative mass. Not only did it match the observed acceleration of the universe, but it also explained the distribution of galaxies and dark matter effects without needing any actual dark energy or dark matter. Just negative mass. Of course, it's still just a theory. No one has directly detected negative mass yet. But the fact that this kind of model even works mathematically shows that we might be onto something much bigger than we realized. And what about laboratory experiments? Has anyone tried to create or detect negative mass here on Earth? The answer is, kind of. In 2017, physicists at Washington State University created a bizarre fluid made of rubidium atoms cooled to near absolute zero, what's called a Bose-Einstein condensate. Under certain conditions, this fluid behaved like it had negative mass. When pushed, it accelerated backwards. That doesn't mean they made real negative mass, but they created something that acts like it, at least in a very controlled setting. It's a hint. A tease. Proof that the universe might allow this kind of behavior under the right circumstances. Now picture where this could all lead. If we crack this mystery, if we figure out how to manipulate or interact with negative mass, it won't just change astronomy. It could flip everything in physics. Propulsion. Energy. Time. Gravity. Even our understanding of reality itself. We might learn how to cancel gravity. Create artificial wormholes. Harness fields that push instead of pull. Or even find ways to reverse inertia, making movement in space as effortless as floating in water. It's a future that sounds like science fiction now. But remember, not long ago, black holes, gravitational waves, and time dilation also sounded like fiction. Until we proved them. One by one. And if negative mass is out there, hiding in the voids, slipping through gravitational fingers, rewriting the rules, then it means our map of the universe is incomplete. Not wrong, but unfinished. Like a painting missing entire colors. A story missing chapters. A machine missing gears. And maybe, just maybe, negative mass is the missing piece we've been searching for. Formation of large-scale cosmic structures, like galaxy filaments and vast voids, without needing to introduce any new particles or fields. Their model, called a negative mass cosmology, was radical. It flipped the script on everything we thought we knew. Instead of explaining the acceleration of the universe with some mysterious dark energy, it suggested that negative mass was doing the job all along. In their simulations, galaxies naturally clumped together, surrounded by vast regions of negative mass that acted like cosmic repellers, pushing everything apart. The result? A universe that looked shockingly similar to our own, without requiring dark energy at all. Now think about what that means. If this model turns out to be right, then dark energy, this mysterious thing that supposedly makes up 68% of the universe, might not be a separate force at all. It might just be the effect of negative mass spread throughout space. We wouldn't need to invent a new kind of energy. We just need to admit that the universe includes negative mass as part of its foundation. And that leads to one of the biggest implications of all. If negative mass is real, and it's widespread throughout the cosmos, then every cosmological theory we have, from the Big Bang to cosmic inflation to the fate of the universe itself, has to be rethought. Maybe the early universe didn't just expand because of an inflaton field or quantum fluctuations. Maybe it expanded the way it did because positive and negative mass were violently repelling each other in a cosmic tug-of-war. That would mean inflation wasn't just a random burst of speed, but the direct result of the universe trying to balance these two opposing forms of matter. Now let's go deeper into the math, because the physics of negative mass isn't just philosophical or speculative. It's rooted in Einstein's field equations from general relativity. Those equations are the blueprint of gravity and space-time, and they don't explicitly forbid negative mass. In fact, when you solve Einstein's equations with a negative mass input, you get solutions that still make mathematical sense. The gravitational field just behaves differently. You can model orbits. You can model expansion. You can even model what happens if you put negative mass next to a black hole. Here's the wild part. A black hole with negative mass, called a white hole in some models, wouldn't suck things in. It would spit things out. It would have repulsive gravity instead of attractive gravity. And because of that, nothing could ever enter it. Information, matter, radiation, everything would be ejected. That's mind-blowing, because it might provide an answer to the black hole information paradox. If negative mass exists and white holes are real, maybe the universe does have a way to preserve and recycle information, instead of letting it disappear forever in a black hole's core. And now we get to what might be the most mind-shattering idea of all, negative mass time travel. Sounds ridiculous, right? But here's how it works. In certain interpretations of general relativity, closed time-like curves, which allow for movement through time, become possible when you introduce exotic matter or negative energy densities. Basically, if you bend space-time enough in just the right way, you can create loops. Loops in time. These wouldn't be just theoretical, they'd be literal pathways through space-time that could, in theory, send an object back to its own past. Of course, this comes with all the paradoxes you'd expect: grandfather paradoxes, bootstrap paradoxes, causality violations. But from a purely physics standpoint, negative mass makes time travel less absurd and more possible. Even if we never build a time machine, the fact that the math doesn't automatically collapse when we introduce negative mass tells us that our universe is far more flexible and strange than we thought. So where does all this leave us? Let's just step back for a second and look at the big picture. We live in a universe that is expanding faster than it should. A universe where 95% of its content is invisible. A universe that behaves like there's something pushing galaxies apart, something we can't see or touch. We've called it dark energy. We've called it the cosmological constant. But maybe, just maybe, it's negative mass, hiding in plain sight, sitting in the voids, shaping everything without ever showing its face. And this idea, once thought to be too weird to consider, is starting to gain traction. More papers. More simulations. More interest. Physicists who used to ignore the concept are now saying, "Wait. Let's take another look." We might be on the brink of a revolution in physics. One that doesn't require us to invent entirely new forces or particles, but one that asks us to embrace a different kind of matter, one that does everything backward. And if that revolution comes, it won't just change how we see the universe. It'll change what we can do in it. We're talking about the potential to tap into a resource that bends gravity the opposite way. That could stabilize wormholes. That could power warp drives. That could rewrite our understanding of time itself. That's not science fiction. That's the logical conclusion of physics that's already on paper. So the next time you look up at the night sky, and you see the dark spaces between the stars, don't think of them as empty. Think of them as filled with possibility. Because in those cold, dark regions of space, in the silence between the galaxies, we might be staring at the most powerful force in the universe. One that doesn't pull us together, but pushes us forward. A force we've only just begun to understand. Some scientists even believe that white holes, theoretical as they are, could be the other side of black holes, connected by wormholes. And guess what's needed to hold that kind of structure together? You got it, negative mass or negative energy. This opens up a disturbing, yet fascinating possibility. What if the universe is filled with hidden portals, connections between distant parts of space and time, but we just haven't been able to detect them yet because we've been looking at everything through the lens of positive mass only? Maybe space itself is riddled with tunnels we've never noticed, paths that have been there since the beginning of time. Maybe some of the strangest anomalies we've recorded, sudden energy bursts, gamma-ray flashes, or stars seemingly vanishing, aren't random at all, but the effects of matter passing through something far more exotic. But there's another twist. Negative mass might not behave the same way everywhere. Some theorists think that negative mass isn't uniform. Instead, it might oscillate, switching between attractive and repulsive depending on density or environment. In low-energy regions like intergalactic space, it might act as repulsive mass. But near massive bodies, it might flip behavior, stabilizing their orbits or even balancing out gravitational collapse. This could explain why we haven't clearly seen it. If it's always reacting to its environment, then its effects would be subtle, complex, and not easily separated from ordinary gravitational forces. It might not appear as a single, clean fingerprint, but as a set of strange, inconsistent clues scattered all across the cosmos. And let's be real, scientists have seen things they can't explain. Galaxies with impossible rotation speeds. Voids that are too large to exist under normal gravity. Regions where gravitational lensing acts in ways that don't quite fit standard models. Usually, they patch the math with dark matter or dark energy. But what if all those patches are just different symptoms of the same deeper truth? We've already tried modifying gravity to explain what we see. We've tried new particles. We've tried unseen forces. But negative mass offers a completely different approach. Not a new. Even tried rewriting the fundamental constants of physics in desperate attempts to make the math match the cosmos. But we've rarely considered that maybe the missing puzzle piece isn't more complexity. Maybe it's something simple but strange, like negative mass. A kind of matter that's been hiding in plain sight, warping reality in subtle ways that we've mistaken for something else entirely. Now imagine this. What if negative mass isn't just real? What if it's common? Imagine that for every galaxy of stars made from positive mass, there's an unseen counterpart structure, made entirely from negative mass, that we can't detect directly, but that still shapes the universe from the shadows. These invisible structures wouldn't emit light. They wouldn't form stars. But they would influence the movements of galaxies, the formation of clusters, and even the expansion of space itself. They would be like cosmic ghosts, present everywhere, but impossible to touch. And it might go even further. If negative mass exists and interacts with gravity differently, then maybe it also interacts with time differently. Maybe it doesn't age the same way. Maybe negative mass doesn't experience time the way we do. In some fringe theories, negative mass particles could move backward in time from our perspective. That's not science fiction. It's based on the real mathematics of relativity and particle physics. There's even a name for them, tachyons. Particles that move faster than light, and, in doing so, appear to move backward in time. So now we've gone from a weird idea to a deeply unsettling one. If negative mass exists, and if it allows time travel, even in the tiniest theoretical way, then the universe might not just be stranger than we imagine. It might be stranger than we can imagine. We could be living in a cosmos filled with particles that defy our sense of motion, time, causality. And we never know, because we're trapped in a small slice of what's really out there. But let's pause for a second. Let's go back to where we started. Space, cold, vast, mysterious. We look up at the stars and think we understand something. We know their ages. We know their compositions. We've mapped galaxies, black holes, quasars. But then you remember, 95% of the universe is invisible. Dark matter. Dark energy. Forces and particles we can't see. It's not that we're missing a piece of the puzzle, we're missing most of the puzzle. And what if negative mass is the key to that hidden 95%? Think about the Big Bang. Most models say the universe started as a singularity, an infinitely dense point of energy. But some alternative models say the universe was born not from a single burst, but from the collision of opposite energies. Positive mass. Negative mass. Slamming together, canceling out in some regions, amplifying each other in others. That kind of beginning could create symmetry. It could explain why the universe is flat. Why it expands. Why it accelerates. All without inventing new fields or particles. And there's more. Negative mass might not just exist in the universe, it might be built into the structure of space-time itself. Some physicists believe that the vacuum of space is not empty, but filled with quantum fluctuations, tiny bursts of energy that pop in and out of existence. These virtual particles could include negative mass components. That would mean space is constantly bubbling with tiny pockets of repulsive gravity, influencing light, time, and matter on the smallest scales. That could explain why the universe is expanding, not because of a force acting from the outside, but because of pressure within the vacuum itself. So where do we go from here? We build better telescopes. We watch for signs of gravitational repulsion. We study the structure of cosmic voids. We look for lensing anomalies. We test models of negative mass cosmology. We ask dangerous questions. What if some black holes aren't what they seem? What if some galaxies are missing because they're made of matter that pushes light away instead of bending it toward us? And maybe someday, we'll stop asking, what if, and start asking, where is it? Because if negative mass exists, if it's real, it's not just a weird side note in physics textbooks. It's the missing skeleton of the universe. The invisible hand shaping galaxies, powering cosmic expansion, and maybe even holding open the doors of space-time itself. Matter and dark energy make up most of what's out there, and we have no idea what they really are. We just know they exist because of how things move, how gravity behaves, how light bends. But what if both of those mysterious ingredients, dark matter and dark energy, are just the shadows of a much stranger reality? What if they're the gravitational side effects of negative mass? Think about that for a second. Dark matter is supposed to be this invisible stuff that holds galaxies together, right? It keeps stars from flying off into space. But we can't find it, can't detect it with any instrument except by how it tugs on things with gravity. But now ask yourself, if negative mass repels positive mass, could a sea of negative mass around a galaxy actually create a kind of pressure that pushes inward? Like an invisible hand squeezing the galaxy, holding it in place, while we mistake that inward effect as extra gravity from an invisible mass? That would look like dark matter, but it's not. It's negative mass pushing instead of positive mass pulling. And now consider dark energy. We know the universe is expanding faster and faster. The only way to explain that with what we see is to say there must be some unknown force stretching space itself. That's where dark energy comes in. But maybe it's not energy at all. Maybe it's the natural result of negative mass repelling everything. Imagine the universe filled with tiny, invisible negative mass particles, and each one is pushing against the fabric of space, against stars, galaxies, everything. Over billions of years, that repulsion would accelerate the expansion of the universe, exactly what we observe. So we're in a strange place now. Negative mass isn't just a fringe idea. It might be the missing piece that makes sense of both dark matter and dark energy. It might be the hidden structure that underpins everything we don't understand about the cosmos. And if that's true, then it changes everything. Our physics. Our cosmology. Even our theories about the birth and fate of the universe. But hold on, because there's more. Let's talk about the biggest mystery of all, the origin of the universe itself. The Big Bang. Scientists say that everything, space, time, energy, matter, all exploded from a single point. But that idea raises a lot of questions. What caused the explosion? What came before the Big Bang? Why did it happen? Here's where negative mass throws another curveball. Some cosmologists believe that if negative mass exists, it could explain the Big Bang in a totally new way. Imagine this. At the beginning of time, there wasn't just a burst of positive energy. There was an equal and opposite burst of negative energy. Like a cosmic yin and yang, perfectly balanced. Instead of everything coming from nothing, everything came from balance. For every bit of matter that flew outward, there was an equal amount of negative matter flying in the opposite direction, creating two universes, connected at birth, but diverging forever. One universe made of positive mass, ours, and another made of negative mass, completely invisible to us, expanding in the opposite direction through time and space. This idea is called a mirror universe, and it's more than science fiction. The equations of physics don't forbid it. In fact, in many cases, they suggest it's not only possible, but necessary. So now we're looking at a multiverse scenario. One where for every action, there's an opposite. For every galaxy here, another made of negative matter over there. For every tick of time forward in our universe, a tick of time backward in the mirror universe. We might never see it. But it could be out there, influencing our cosmos in invisible ways, tugging on the edges of existence, bending the laws of physics just enough to make us wonder. And guess what? This could even explain why our universe looks the way it does, why the fundamental constants of nature seem so perfectly tuned for life. Maybe it's not just random. Maybe the negative mass universe has the opposite constants, ones that would make life impossible. But together, both universes maintain balance. One gives, the other takes. One expands, the other contracts. One runs forward, the other runs backward. We're not done. Not even close. Because now we have to ask, if negative mass is everywhere, and if it bends space, moves in weird ways, and possibly even interacts with time differently, then maybe, just maybe, it's the key to unlocking faster-than-light travel. That's not a fantasy. In fact, the idea has been seriously considered by physicists working on warp drive theories. The Alcubierre drive, for example, is a theoretical engine that would bend space around a spacecraft, shrinking the space in front of it and expanding the space behind it, allowing the craft to effectively ride a wave through space-time. The equations for this drive require negative mass, or more precisely, negative energy density, to work. Why? Because bending space that way isn't possible with normal matter. You need something that pulls space in instead of pushing it out. Something that breaks the rules without breaking reality. Negative mass could do that. If we could isolate it, stabilize it, and harness it, we could create a bubble of space around a ship, and that bubble could move faster than light, without violating Einstein's relativity, because the ship itself wouldn't be moving through space, space would be moving around the ship. We're talking about a real-life warp drive. A way to travel to distant stars in weeks instead of centuries. And it all hinges on negative mass. But before we get too excited, we have to face the hard truth. Right now, we don't know how to create or capture negative mass. We've never observed it directly. But we've seen signs. Strange gravitational behaviors. Unexplained anomalies. And in 2017, physicists at Washington State University created a fluid with negative effective mass under extreme conditions. It wasn't true negative mass, but it mimicked some of its behaviors. That's a start. The frontier is open. And the questions are bigger than ever. Energy, matter, exploded into existence from a single, infinitely dense point about 13.8 billion years ago. But here's the uncomfortable truth. No one really knows why it happened, or what existed before it, or even how something can come from nothing. All we know is that, somehow, everything we see, all the galaxies, stars, planets, atoms, came from a moment of unimaginable density and heat. But where did that energy come from? Now imagine if the universe was born not from nothing, but from balance. Imagine that the total amount of mass in the universe is zero. That sounds crazy, right? But not if you think of positive mass and negative mass as two sides of the same coin. What if the universe spontaneously formed out of a perfectly balanced equation? For every bit of positive mass and energy that went into making stars and galaxies, there was an equal and opposite amount of negative mass that emerged with it, forming invisible regions of the cosmos that have been repelling, shaping, and hiding from us ever since. It would explain so much. It would mean the total energy of the universe is zero, and that's something physicists have actually proposed. If negative mass exists, it could cancel out the positive mass. It could mean that the universe is not a chaotic accident, but a balanced fluctuation, a kind of cosmic symmetry, one we just didn't know how to see before. And maybe this explains why the universe expands. Not because it was flung apart like shrapnel, but because negative mass and positive mass are still pushing away from each other, still locked in a dance across cosmic distances. Each type of matter obeying its own rules, interacting only faintly with the other, creating the illusion of an expanding space, when in reality it's two worlds pulling apart. But this raises a new question. If there are negative mass regions in space, where are they? Are they scattered like islands across the universe, hiding between galaxies? Are they clustered in the vast, empty voids where no stars shine? Or are they closer than we think, hovering just outside the boundaries of our instruments, pressing in invisibly on our world? Some theorists have speculated that these negative mass regions might fill the cosmic voids, the massive, Empty spaces between galaxy clusters. These voids aren't just a little empty, they're huge. Some are hundreds of millions of light years across, with barely a trace of matter. It's as if something is pushing the galaxies away from those regions. That something could be negative mass. Picture this, a galaxy cluster surrounded by a vast halo of negative mass. The positive mass in the galaxies pulls inward, and the negative mass around it pushes outward. The result? A stable balance that holds the galaxy together. Meanwhile, those voids stay empty because any matter that drifts into them gets pushed out again by the repulsive pressure of negative mass. But the effects might go even further. Imagine a spacecraft traveling through space. As it crosses into a region where negative mass dominates, it might begin to decelerate, not because of friction, but because the very fabric of space is pushing against it. Or worse, it might start behaving unpredictably, as gravitational rules begin to reverse. Light might bend strangely. Time might flow differently. We might see mirages in space, not of light, but of gravity itself, creating distortions we can't explain. And now, let's take this even deeper. What if the reason we haven't detected negative mass yet is because we're using the wrong tools? All our instruments, from particle accelerators to telescopes, are built to detect things that behave like us. Like positive mass. They look for particles that attract, that have energy, that obey the rules we're used to. But negative mass doesn't play by those rules. It could slip through detectors. It might cancel out signals. It could be hiding in the data we've already collected, data we misunderstood because we assumed the universe was only made of one kind of stuff. And the implications? They're mind-bending. Because if negative mass is real, then all of our understanding about black holes, time travel, wormholes, and cosmic evolution has to be rethought. The very structure of the universe, from quantum fields to galactic superclusters, would need to be reimagined. And we're just getting started. Those enormous gaps that stretch for hundreds of millions of light years, where almost no galaxies exist. To the naked eye, or even to our most powerful telescopes, they appear completely empty. But what if they're not empty at all? What if they're full of negative mass, creating a vast, unseen web that surrounds and influences the structure of the entire universe? This would flip everything we think we know on its head. Cosmic voids might not be empty gaps between clusters of matter. They might actually be the home of something we've never been able to detect, a kind of invisible anti-gravity ocean. These negative mass regions would push outward on the galaxies surrounding them, creating the large-scale structure we see today, galaxies clustering into long, thin filaments and sheets, like cosmic soap bubbles, all separated by enormous voids. But these voids wouldn't be passive gaps, they'd be active, shaping the universe from the shadows. And the galaxies? They'd be like ships floating on the edges of these invisible seas, drawn into long lines and clusters not just by gravity, but by the invisible pressure of negative mass pushing them together from behind. We'd see this as dark matter. We'd think it's gravity pulling things together, but really, it's anti-gravity pushing them from the other side. Now this is where it gets even stranger. If these negative mass regions really do exist, and if they've been shaping the universe since the very beginning, then they're not just a curiosity, they're fundamental. They might be older than the galaxies themselves. They might have formed before stars, before atoms, before anything we can see today. They might be remnants of a deeper structure of reality, something baked into the very fabric of space and time. And there's another weird possibility. What if negative mass isn't just out there? What if it's here, right now, in our own part of the universe? Think about the Pioneer anomaly. Back in the early 2000s, scientists noticed something strange with the Pioneer 10 and 11 spacecraft. As they drifted farther from Earth, they started to slow down ever so slightly. Not because of gravity from the sun, not because of anything we expected. It was small, but measurable. For years, people argued about it. Thermal emissions? Software error? Eventually, they mostly wrote it off as a heat imbalance pushing the craft slightly. But some physicists raised another possibility. What if the spacecraft were moving through a region of negative mass? That would do it. As we said earlier, negative mass and positive mass repel each other. So if the spacecraft were surrounded by tiny amounts of negative mass, it would push back against them, like flying into a wind we couldn't see. It would look like a tiny deceleration, even if there were no particles or gas in the way. And if that's true, then negative mass might not be something far away in deep space. It might be right here in our solar system, thin, diffuse, invisible, but real. Now let's take that further. If negative mass can influence spacecraft, could it also influence us? Could it have effects on Earth we haven't even noticed? There are strange gravitational anomalies that scientists still don't fully understand. Tiny deviations in measurements, inconsistencies in satellite orbits, fluctuations in gravitational constants that vary slightly depending on location. These have always been dismissed as noise or error. But what if they're not? What if we're occasionally brushing up against tiny clouds of negative mass? And then, of course, comes the question we have to ask: can we use negative mass? If we ever found a way to detect it directly, to harvest it, or create it, the possibilities are mind-blowing. The most obvious? Propulsion. Negative mass would break the rules of Newtonian mechanics. Here's how: if you push on a negative mass object, it moves in the opposite direction of the force. That sounds insane, but it's a mathematical consequence of how negative inertia would behave. Imagine you strap a negative mass block to a positive mass spacecraft and connect them somehow. You push them, and they start accelerating forever, without using any fuel. This concept is known as a negative mass drive, or Alcubierre-type engine. The idea is that a positive and negative mass system, interacting through a stabilizing mechanism, could generate constant acceleration, bypassing the need for traditional fuel. You could reach near light speeds, or even create space-time distortions, the basis for the so-called warp drive. Now, to be clear, this isn't just sci-fi fantasy. The equations of general relativity allow for negative energy densities, exotic matter that bends space-time in the opposite way. And the famous Alcubierre warp drive is built on exactly this idea, that if you can generate a region of negative energy, you can create a warp bubble that contracts space in front of you and expands it behind. You don't break the speed of light, you just ride a distortion in space-time. The problem? We don't know how to make that kind of negative energy, at least not yet. But if negative mass regions already exist in space, that could change everything. Maybe we don't have to create negative mass. Maybe we just need to find it, tap into it, and harness it. Now let's imagine that happens. Let's say in the next 100 years, we develop technology sensitive enough to detect negative mass in the cosmos. And then we find a region, maybe in deep interstellar space, maybe in a cosmic void, maybe even close to Earth. What happens next? First, we study it. We probe it with instruments, measure its effects. We build spacecraft designed to interact with it. Maybe we launch drones into it, and watch how they move. Maybe they accelerate unexpectedly. Maybe they vanish. Maybe they come back with strange data, warp time readings, distorted mass sensors, unexplained radiation. Then we get bolder. We build experimental drives, ships that use negative mass to create thrust without fuel. They launch, and they work. Suddenly, interstellar travel isn't just a dream. It's happening. We send missions to the stars. And then, we go further. We use negative mass to bend space-time itself. We create small warp bubbles, tiny at first. Then bigger. Controlled. Stabilized. We build gateways, shortcuts through space, based on regions of intense negative energy. We call them wormholes. We create corridors through the universe, linking distant star systems. Humanity becomes a space-faring civilization, all because of negative mass. But the story doesn't end there. Because if negative mass exists, and if we learn to use it, then we're not the only ones who could. Other civilizations, if they exist, might have discovered it long before us. They might have harnessed it millions of years ago. They might be using it right now, traveling, hiding, shaping space. And maybe that's why we haven't seen them. Maybe the reason we haven't detected alien life isn't because it's rare, but because it's using negative mass technology to hide. Think about it. Negative mass can bend light, distort gravity, and create space-time bubbles. An advanced civilization could literally cloak itself behind a negative mass shell. Its ships could be invisible. Its signals warped. It could be sitting just beyond the edge of our solar system, and we'd never know. And if that's true, what was causing it? Some blamed thermal radiation. The idea that heat escaping from the spacecraft in one direction gave it a tiny push in the other. And while that explanation might cover part of the anomaly, it doesn't fully rule out more exotic ideas. One of those ideas? That the spacecraft were moving through, or being influenced by, regions of negative mass. If negative mass exists in localized pockets, especially in the far reaches of the solar system or beyond, it could subtly repel objects like spacecraft. Imagine it like sailing through water that has strange currents. You'd feel forces acting on you that you didn't expect. These forces wouldn't need to be strong, they just need to be consistent and unexplained. And that's exactly what the Pioneer spacecraft experienced. But it's not just about distant probes. There have been other unexplained anomalies in space, things that might hint at something deeper going on. Galaxy rotation curves are a big one. For decades, we've seen galaxies rotating far too fast at their edges. The stars there should be flung away into space, but they're not. Our answer to this has been dark matter, an invisible substance that holds everything together with its gravity. But what if, instead of an unseen pull, it's an unseen push? What if negative mass outside the galaxy is pressing in, keeping those stars from drifting away? This flips the whole script. It takes what we thought was attraction and reimagines it as repulsion, not less physics, but different physics. And once you start thinking about it like that, so many other mysteries begin to shift into a new light. Let's go deeper. The idea of negative mass isn't just theoretical fantasy. Physicists have actually created it in the lab, at least in a limited, simulated form. In 2017, researchers at Washington State University managed to create a fluid with negative effective mass using a type of ultra-cold matter called a Bose-Einstein condensate. When they pushed this fluid, it didn't accelerate in the direction of the force like normal matter. It moved backwards. That's exactly what negative mass should do. Now, this doesn't mean we've found negative mass as it might exist in the cosmos. What it does mean is that nature can support behavior that looks just like it. And if we can create it here, even in a controlled setup, that makes it a little easier to imagine it happening naturally on a cosmic scale. But it gets even crazier. Let's talk about wormholes. Theoretical bridges between two distant points in space and time. According to Einstein's general relativity, they're possible, but they're unstable. They'd collapse instantly unless something keeps them open. And the one thing that could do that? Negative mass. Or more specifically, something called exotic matter, matter with negative energy density. If negative mass regions exist in space, they could be more than just invisible seas shaping the universe. They could be gateways. They could be the key to stabilizing wormholes, making faster-than-light travel more than just a science fiction fantasy. These regions might even act as natural wormhole anchors, holes in the fabric of reality where space bends so sharply that two distant regions become one. That would explain a lot. It would explain why some areas of space seem to bend light in ways we don't understand. Gravitational lensing with no visible mass. It would explain sudden, high-energy phenomena we can't trace. It could even explain strange cosmic objects that don't behave like anything we've ever seen. Because maybe they're not objects at all. Maybe they're windows. And here's the chilling part. If negative mass really does exist, and if it behaves the way theory predicts, it would move toward us when we move away from it. That means if you ever tried to get away from it, it would chase you. Not because it's alive, but because of the weird, upside-down physics it follows. Every force you apply to it makes it move in the opposite direction. It's like a cosmic shadow that resists control, resists escape. Now ask yourself, if such regions are out there, what happens when we send probes or signals in their direction? Do they get deflected? Swallowed? Reflected back in some unknown form? Could negative mass regions be responsible for the strange silences we've encountered in the search for extraterrestrial life? The Great Silence that haunts SETI researchers. We send out signals expecting straight lines and clear echoes, but what if the signals never get there? What if they're distorted or scattered by regions of space that don't follow our rules? What if we're looking into the abyss, and it's bending the light before it reaches our eyes? That brings us to another strange phenomenon: fast radio bursts. These are incredibly powerful, millisecond-long blasts of radio waves coming from deep space. We don't know exactly what causes them. Some repeat, some don't. They show up randomly, briefly, and vanish. What if they're signals, not from life, but from reality itself? What if they're echoes of interactions between normal and negative mass? Sudden compressions or releases of energy as these two worlds brush up against each other? Maybe we're seeing the tip of an invisible iceberg, brief flashes when two universes touch. And yes, it's entirely possible that negative mass regions are not just patches of space, but separate realms, behaving like shadows of our own universe. Always near us, but never fully overlapping. Think about the multiverse. The idea that there are countless other universes, each with its own laws. What if negative mass regions are those other universes, intersecting with ours in only the faintest, most mysterious ways? What if we're sharing this space with another kind of matter entirely, one that doesn't interact with us through light, heat, or touch, but still affects the shape of our cosmos? And here's the kicker. If negative mass exists, and if it's truly as foundational as some believe, then our entire model of physics, cosmology, and even time could be built on an incomplete story. We're like fish trying to understand the ocean without knowing currents exist. Everything we measure, everything we assume, everything we think we've proven, it might be missing half the picture. Dark energy, dark matter, expansion, void structures, the silence of the universe, the nature of gravity, the formation of galaxies. All of it might be shaped by a force we've never directly seen. But now, more and more scientists are starting to ask the question, what if we've seen it all along, and just didn't recognize it? Can simulate it in a lab, even in a limited way, then it's not just science fiction anymore. It's science fact, and that changes everything. Because if negative mass behavior is possible under the right conditions, maybe it's not so rare out in the universe. Maybe it forms naturally under extreme conditions, like in the early universe, or inside black holes, or at the edge of cosmic voids. Maybe it's not even a separate form of matter, but a property of space itself, like a hidden layer underneath what we usually see. Think of it like this. Just as dark energy seems to stretch space outward and dark matter seems to hold galaxies together, negative mass could be the third hidden actor, working from the shadows, bending the rules in ways we haven't even started to fully grasp. And here's a mind-bending idea. What if negative mass is connected to faster-than-light travel? One of the biggest problems with faster-than-light travel is that it seems to violate the laws of physics. Nothing with mass can go faster than the speed of light. That's a basic rule of Einstein's theory of relativity. But negative mass plays with those rules. In fact, there's a theoretical concept known as the Alcubierre drive, a kind of warp drive that could, in theory, allow faster-than-light travel by compressing space in front of a ship and expanding it behind. And guess what kind of matter you need to make that happen? That's right, negative mass. Negative mass would be the fuel that makes warp drives work. Not by pushing a ship through space, but by bending space around it. The ship itself wouldn't move faster than light. It would just ride a wave of distorted space-time. And that wave? It would be powered by negative mass or negative energy density. It's still incredibly theoretical. But if we ever do find naturally occurring negative mass in the universe, it might not just explain strange cosmic behaviors. It might give us the key to breaking the limits of space travel. But we're not done yet. Because if negative mass is real, it also raises terrifying possibilities. One of them is vacuum decay, a catastrophic event that could wipe out everything in an instant. This comes from quantum field theory, which says that the vacuum of space might not be completely stable. There might be a lower energy state out there, a true vacuum, and if the universe ever drops into that state, everything changes. Particles, forces, even the laws of physics could be rewritten. And here's where negative mass comes in. Some physicists think that if regions of negative mass exist, they might trigger this kind of vacuum decay. That's because negative mass represents a different kind of energy configuration. If one of these regions ever collided with normal space, or if it existed long enough to destabilize its surroundings, it might cause a chain reaction, converting the universe to a new state of being in a flash. Lights out, everywhere, forever. But before we panic, let's be clear, this is incredibly speculative. There's no evidence that it's happening or that it can happen. But the fact that negative mass could theoretically lead to the collapse of reality shows just how powerful and mysterious it really is. This isn't just a strange idea from physics textbooks. It's a force that, if it's real, could reshape everything from the Big Bang to the fate of the universe. And here's the final twist in this part of the puzzle. What if dark energy, the mysterious force that's causing the universe to expand faster and faster, isn't some strange, undefined thing? What if it is negative mass? Some physicists have proposed that if negative mass is spread evenly throughout the universe, it would create exactly the effect we see from dark energy, a gentle, consistent repulsion that pushes galaxies apart. And if this negative mass was created at the birth of the universe, or even before it, then it might be the most ancient ingredient in all of reality. Older than light. Older than time. A shadow force that's been hiding in plain sight, holding everything together by pushing it apart. It's wild. It's weird. And it might be real. Lurking beneath the reality we know, a more true vacuum. And if a bubble of that true vacuum were ever triggered, it could expand at the speed of light, rewriting the laws of physics as it goes. Everything, matter, energy, even the fundamental constants, would change. Life wouldn't just die. It would become impossible in any form. Now here's where negative mass comes into this. Some theories suggest that the presence of negative energy, or negative mass, could be exactly the kind of disturbance that destabilizes our current vacuum. If regions of space with negative mass exist, especially in places where high-energy events are already occurring, like around black holes or in the early universe, then these areas might act as seeds for vacuum decay. And what's really chilling? We wouldn't see it coming. Since it would move at the speed of light, there would be no warning. No signal. Just nothing. One moment we're here, the next moment the laws of physics flip, and we're gone. That might sound like pure horror, but it also shows just how deep the mystery of negative mass goes. It isn't just some strange mathematical quirk, it could be tied to the very fabric of existence, and whether that fabric is stable at all. Now let's pull back for a second. We've talked about how negative mass could affect galaxies, space travel, vacuum stability, and even the structure of space itself. But what about time? Could negative mass have something to do with time travel? According to general relativity, time and space are not separate things. They're part of the same structure, space-time. And if you can warp space, you can warp time. Theoretical physicist Kip Thorne, who advised on Interstellar, showed that if you had two wormholes and moved one at relativistic speeds, you could create a time difference between the mouths. If you then went through the wormhole, you could travel back in time. But there's a catch. To hold a wormhole open, you need negative energy, the kind of stuff that negative mass might create. That means that if negative mass exists, and can be harvested or found naturally in the universe, then the ingredients for time travel might actually be out there. Not in the science fiction sense of hopping into a DeLorean, but in the sense of stable wormholes or curved loops in space-time. This possibility is one reason physicists haven't completely ruled it out, because the math doesn't forbid it, it just demands a very exotic ingredient. And that ingredient might just be hiding out in the vacuum between stars. And then there's cosmology, the study of the entire universe. Some researchers have proposed that the entire expansion of the universe, which we currently attribute to dark energy, might instead be explained by negative mass. Imagine that, instead of a mysterious repulsive force stretching space, what we're actually seeing is a kind of runaway, motion caused by a mix of positive and negative mass. In such a scenario, the universe wouldn't be made of just galaxies and voids. It would be made of gravitational push-pull pairs. These pairs would act like a kind of cosmic engine, driving acceleration without the need for a separate dark energy field. This kind of thinking is radical, sure, but it's not baseless. In 2018, physicist Jamie Farnes proposed a model in which negative mass particles could naturally produce the effects we currently attribute to both dark matter and dark energy, solving two of the biggest mysteries in physics with one explanation. And while the model is still controversial and hasn't been fully tested, it's a sign of just how important negative mass could be if it turns out to be real. Let's go even deeper. We've been assuming that negative mass is something rare, something on the edges of physics. But what if it's not? What if negative mass is common, but we just can't see it? What if, right now, we're swimming through a universe full of negative mass, and we don't notice it because it interacts with us in ways we can't easily detect? Remember, gravity is a weak force. You need a whole planet to feel it. If there were clouds of negative mass spread across space, they might influence motion subtly, distorting light, bending space-time, changing the behavior of particles, without leaving behind obvious signs. Maybe the strange rotation of galaxies isn't the only clue. Maybe gravitational lensing, where light from distant galaxies is bent, also shows hints of something else. Or maybe some of the empty regions in the universe aren't empty at all, but full of repulsive mass that's quietly shaping everything around it. Think about that. What we call the cosmic web, a vast network of galaxies, filaments, and voids, might not just be shaped by regular gravity. It might be shaped by something more complex, a kind of invisible scaffolding made of negative mass. The filaments might be like cosmic highways of regular matter, while the voids are repulsion zones, kept clear by hidden patches of negative mass. That would change everything we thought we knew about cosmic structure, and it would open the door to new physics. Now let's talk about black holes. These are already some of the most extreme objects in the universe. Regions where gravity is so strong, not even light can escape. But there's a problem. According to current physics, black holes should evaporate over time through a process called Hawking radiation. But when they evaporate, what happens to the information that was inside? Does it get destroyed? That's something physics says shouldn't happen, and yet, we don't know how it's preserved. It's called the black hole information paradox. Some researchers have suggested that negative mass might be part of the answer. If negative mass can exist near the event horizon, the boundary around a black hole, then it might help balance the equations. It could even create exotic phenomena like white holes, the theoretical opposites of black holes that expel matter instead of sucking it in. These have never been observed, but they're allowed in the equations. The problem is keeping them stable, and guess what you need to do that? Negative mass. So it's not just a question of, does negative mass exist? It's more like, if it exists, what doesn't it touch? Because the more you follow this rabbit hole, the more you realize it's tied to nearly every big mystery in cosmology. From how the universe formed, to how it will end, to whether time travel is possible, to whether wormholes can be stabilized, to how galaxies stay together, to what happened in the first split seconds of the Big Bang. Negative mass might be the hidden thread running through them all. And here's another twist. If negative mass exists, it might even suggest that our universe isn't the only one. In some theories of the multiverse, where our universe is just one of many, different universes can have different physical constants, different particles, and even different forms of mass. Maybe in some of them, negative mass dominates. Maybe we live in a kind of boundary zone between different mass polarities. And maybe the strange phenomena we see in our universe, from dark energy to unexplained anomalies, are the result of interactions with other, hidden layers of reality. Layers filled with mass that pushes instead of pulls. And now here's where it gets really weird. Quantum physics, the science of the very small, is all about probability and uncertainty. But general relativity, the science of the very large, is all about certainty and curvature. For decades, physicists have been trying to reconcile these two worlds. What if negative mass is part of the answer? Some researchers have proposed that vacuum fluctuations, tiny, random changes in energy in empty space, might involve negative energy. These fluctuations are happening everywhere, all the time. And if they sometimes dip into negative mass territory, even for a fraction of a second, then that might help explain how the universe stays stable, or how it evolves in unpredictable ways. So here we are. We started with a strange idea: what if mass could be negative? And now we're staring into the heart of nearly every cosmic mystery. Because negative mass isn't just a weird trick of math. It might be the missing piece, the thing that ties together gravity, expansion, dark matter, dark energy, wormholes, black holes, and the quantum world. It might explain things we haven't even discovered yet. Or it might be the next giant leap, the next revolution in physics, waiting just around the corner. Space-time that let information, or even objects, loop back to earlier moments. That's not just wild speculation, it's grounded in the math of general relativity. The equations don't forbid time travel, they just require extreme and exotic conditions to make it happen. And negative mass could be the golden ticket. It could keep wormholes open, stabilize space-time curves, and even make closed time-like curves, CTCs, possible, paths through space-time that loop back to their own beginning. But here's where things get really strange. Time travel introduces paradoxes: the grandfather paradox, the bootstrap paradox, and all the mind-melting thought experiments that come with them. If negative mass enables time travel, then the universe would need to have some kind of mechanism to deal with paradoxes. Maybe that's why negative mass regions are so rare. Maybe the universe is self-correcting, hiding or neutralizing negative mass to avoid letting causality break down. And still, there's more. Negative mass might not just be something exotic and rare, tucked away in hidden corners of the cosmos. Some scientists are now proposing that the universe is filled with it. That it's all around us, woven into the cosmic web, balancing out positive mass like a cosmic yin and yang. A few radical theories even suggest that dark energy is a form of negative mass, not something separate, but the other side of the cosmic coin. That could explain why the universe is accelerating. Negative mass would repel everything around it, creating a kind of cosmic anti-gravity effect that makes galaxies speed away from each other faster and faster over time. And it would mean the universe isn't expanding into nothing, it's expanding into a field of negative mass that's been there from the beginning. That would fundamentally change how we think about the Big Bang, the fate of the cosmos, and even what nothing actually means. Maybe the vacuum of space isn't empty at all. Maybe it's packed with negative mass particles constantly pushing outward, invisible to our detectors but shaping the cosmos on the largest scales. In fact, there's a new breed of scientists working on mathematical models that include negative mass as a standard part of physics, not just an exotic idea, but a requirement for the equations to work. These models can explain why galaxies don't spin apart, why cosmic voids are so massive, why the cosmic microwave background is slightly lopsided. Negative mass, in these views, becomes not just possible but necessary. The missing ingredient in the recipe of the universe. And it gets deeper still. Imagine a particle with negative mass. Let's say you try to push it. In normal physics, when you apply a force to an object, it moves in the direction you pushed. But with negative mass, it would accelerate in the opposite direction of the force. So if you tried to push it away, it would come toward you. That creates a totally alien kind of behavior, one that breaks our normal sense of cause and effect. It's not just weird, it's potentially revolutionary. Because if we could isolate and manipulate these particles, they could become the basis for new technologies, propulsion systems, gravity control, maybe even quantum computing systems that exploit their strange physics. You could pair a positive mass and a negative mass particle together, and in theory, they would form a runaway pair, constantly accelerating in one direction without any input of energy. That's free energy. That's an engine that runs forever. It violates everything we thought we knew about thermodynamics, and yet, it fits perfectly in the equations. Of course, There's a reason we haven't built negative mass engines yet. We don't have the stuff. Or more likely, we don't know where it is, or how to contain it. Negative mass particles might be so unstable, or interact so strangely with regular matter, that they can't be stored in normal containers. They might fall through regular matter, or annihilate it, or even just slip through dimensions we don't yet understand. Which brings us to another fascinating idea: maybe negative mass isn't part of our universe at all. Maybe it leaks in from parallel universes, mirror realities that sit right next to ours in the quantum foam. Think of the multiverse like a layer cake, each universe stacked on top of the other, each with its own physical rules. In some of these layers, mass could be negative by default. Gravity could repel instead of attract. Time could flow backwards. And under just the right circumstances, like black hole singularities or quantum tunneling events, those layers could touch. When they do, maybe a little bit of negative mass leaks through. This would explain why negative mass is so elusive, why we can't detect it directly but see its fingerprints everywhere. It's not from here. It's an intruder from a neighbor universe, slipping through cracks in reality, warping space just enough to bend galaxies and stretch time without revealing itself. And if that's true, what else could be slipping through? Maybe negative mass is just the beginning. Maybe it's the first clue that our universe isn't alone, that it's just one bubble in an infinite sea of possibilities. And maybe, if we keep looking, we'll find more evidence. More phenomena that don't fit in the standard model. More anomalies that point to deeper layers of reality. And one day, we might not just theorize about these things, we might use them. Harness them. Build technologies around them. Even travel between universes. But before we get too far ahead, we have to answer one key question: how do we detect negative mass? How do we actually prove that it's out there? And that's where things get incredibly tricky. Because you can't just look through a telescope and see negative mass. It doesn't glow. It doesn't emit radiation. It might not even interact with light the way regular mass does. But what it does do is influence gravity. And gravity, as weak as it is, leaves fingerprints, in the motion of galaxies, in the curvature of spacetime, in the shape of cosmic voids. That's why astrophysicists are now turning to massive surveys of the sky, tracking the movement of galaxies across billions of light years, looking for tiny irregularities that don't make sense, subtle hints that something is pushing when it should be pulling. Some models predict that negative mass could cluster in specific ways, forming invisible halos around galaxies or sitting in the empty space between galaxy clusters, creating a strange kind of gravitational lens that warps light differently from positive mass. If we find those lenses, and if we can map them, we might finally have a direct line on negative mass. There's also work being done in particle physics labs, places like CERN, where scientists are smashing particles together at unimaginable speeds, trying to create miniature black holes, strangelets, or other exotic particles that might behave like negative mass. So far, no confirmed results, but that doesn't mean it's not real. It just means we're still learning how to ask the right questions. Because the universe doesn't give up its secrets easily. But once it does, once we find even a shred of real negative mass, everything will change. And why the distribution of galaxies forms a kind of web-like structure that stretches across the observable universe. In these models, negative mass isn't just a weird possibility, it's a necessary ingredient that keeps everything coherent. And here's a weird thought: if negative mass particles are real and spread throughout space, they might be constantly interacting with the positive mass particles we're made of. Not through normal collisions, but through subtle repulsive forces that we haven't learned to measure properly yet. Some researchers think this invisible tug-of-war might explain anomalies we see in spacecraft trajectories, or the way satellite orbits decay over time. Others believe it could even help us understand why quantum particles sometimes behave unpredictably. Maybe there's a whole negative mass world affecting quantum behavior in ways we can't detect directly. Let's talk about the math for a second, but in a way that makes sense. In physics, mass shows up in Newton's second law, F equals ma. That means force equals mass times acceleration. If you apply a force to a positive mass, it accelerates in the direction of the force. Easy, right? But if you do that to a negative mass, the math flips. It accelerates in the opposite direction. It's almost like pushing someone and watching them fly toward you instead of away. That's the core weirdness of negative mass. It doesn't obey our intuitive rules of push and pull. And that leads to something even more bizarre. If you place a positive mass next to a negative mass, they would accelerate together forever. The positive mass attracts the negative mass, and the negative mass repels the positive mass. But because of how their masses interact, they don't cancel out. Instead, they create what physicists call a runaway motion. They just keep going, faster and faster, without any extra energy input. If that could be harnessed, it would rewrite everything we know about propulsion, energy, and motion. Now, imagine what that means for space travel. Right now, space travel is brutally inefficient. Rockets have to carry massive amounts of fuel just to escape Earth's gravity. Interstellar travel is a distant dream. But if negative mass exists and could be controlled, we could build propulsion systems that don't require fuel in the traditional sense. You could use negative mass to push a spacecraft forward while the negative mass pulls it in the opposite direction, and because of the way negative mass behaves, the two would accelerate together without using up any fuel. It's the closest thing to a perpetual motion machine physics has ever entertained, and that's saying something. Some speculative designs have already been proposed. One idea is a negative mass halo drive, where a spaceship emits a stream of negative mass particles in the opposite direction it wants to travel. Because of the runaway motion effect, the spaceship and particles would accelerate indefinitely, with no energy cost. Another involves using negative mass to warp spacetime, creating a kind of warp bubble, similar to the Alcubierre drive, a theoretical faster-than-light engine that doesn't break the speed of light because space itself is moving. But we're not there yet. We don't even know if negative mass exists in the real world, only that the math allows it, and the universe might be giving us subtle clues. Let's talk about one of those clues. Back in 1998, two teams of astronomers discovered something that shocked everyone. The expansion of the universe wasn't slowing down, it was speeding up. That discovery led to the idea of dark energy, a mysterious force that makes up about 68% of the universe and is somehow pushing galaxies apart. No one knows what dark energy really is. It doesn't emit light, it doesn't clump, it doesn't seem to interact with matter in any normal way. It's just there. But what if dark energy is just the effect of a universe filled with negative mass? In 2018, physicist Jamie Farnes proposed a model where the universe contains both positive and negative mass, and the negative mass spreads out over time, creating the repulsive effect we see as cosmic acceleration. In his model, negative mass constantly repels itself, forming voids and clusters that influence the motion of galaxies. It's a bold idea, and not everyone agrees with it, but it solves some big problems with dark energy. More importantly, it brings negative mass out of the realm of speculation and into actual testable science. Let's go even deeper. If negative mass exists, then the way we understand gravity might be completely upside down. Right now, we think of gravity as an attractive force, mass pulls on mass. But negative mass could introduce repulsive gravity, a kind of anti-gravity. That isn't just science fiction. If the universe is filled with regions of repulsive gravity, then the structure of everything, from stars to superclusters, would be shaped by this unseen influence. Some cosmologists believe this might explain why galaxies form in filaments and sheets instead of randomly. The idea is that positive and negative mass repel each other, and over billions of years, they form complex patterns. Positive mass clumps into galaxies and clusters, while negative mass fills the gaps and pushes everything apart. It's like an invisible scaffolding that gives the universe its shape. But detecting it? That's the real challenge. Negative mass wouldn't emit light. It wouldn't reflect it either. It might not even bend light in the same way normal mass does. In fact, it could reverse gravitational lensing. Instead of magnifying background objects, it might distort them in the opposite direction. If we ever observe that kind of effect, an anti-lens, it might be the first direct sign of negative mass. Some astronomers are now combing through old telescope data, looking for signs of this exact phenomenon. Others are trying to create negative mass in the lab. In 2017, researchers at Washington State University managed to simulate a negative mass environment using a cloud of rubidium atoms cooled to near absolute zero. When they nudged the atoms, they moved toward the force instead of away, just like a negative mass would. It wasn't true negative mass, but it showed that under the right conditions, we can mimic the behavior. That's a huge step forward. It means we're not just guessing anymore, we're experimenting. We're testing the edges of physics, trying to find the seams where reality might tear open and show us what lies beneath. And maybe that's the biggest mystery of all. Because if negative mass is real, not just in equations, but out there in the cosmos, then we've only just begun to scratch the surface of what's possible. It could mean new physics, new forms of matter, new rules for energy, motion, and time. It could mean the universe is far stranger, more dynamic, and more full of possibilities than we ever imagined. And maybe, just maybe, it's already out there, hiding in the shadows of galaxies, whispering through the void, warping space and time in ways we've yet to understand. The ship from behind, all without expelling any mass or burning any fuel. That's not just a fantasy. It's called a negative mass propulsion system, and the theoretical groundwork has already been laid. Imagine this. Instead of a rocket burning tons of fuel just to escape Earth's atmosphere, a spacecraft could simply interact with a region of negative mass and begin accelerating, indefinitely. The ship and the negative mass would move together in what's called a runaway pair. As long as the system is stable, the motion could continue forever, limited only by relativistic effects like time dilation or the ship's structural limits. Now, that raises massive questions. Could we one day build a spacecraft that can travel faster than light, not by breaking the universal speed limit, but by bending space around itself using negative mass? That's the whole concept behind the Alcubierre warp drive, a theoretical model of faster-than-light travel. And here's the kicker, negative mass is the key ingredient. Without it, the equations don't work. You need something with negative energy density to stretch spacetime in front of the ship and compress it behind, creating a warp bubble that moves space itself faster than light, while the ship inside stays still relative to the bubble. If that sounds familiar, it's because it's straight out of science fiction, but grounded in real, peer-reviewed physics. NASA has even looked into the idea, with the EagleWorks team exploring ways to detect and potentially generate tiny warp bubbles using advanced electromagnetic fields. It's early, very early, but the science isn't off the table. And if negative mass exists in the universe naturally, in regions we haven't explored yet, then the universe may already have its own warp drives. Massive objects traveling through space without any visible propulsion, just riding on the bizarre physics of exotic matter. Let's go deeper. If there are negative mass regions scattered across the cosmos, they might not be uniform. Think of them like patches of turbulence in the air, invisible, unpredictable, and incredibly powerful. A spacecraft that stumbled into one might experience sudden changes in velocity, bizarre distortions in time, or even gravitational lensing from behind, the exact opposite of how gravity normally bends light. If light passed near a negative mass object, it would bend away from it, not toward it. That's an observable signature. And some astronomers think we've already seen hints of this, unexplained lensing events where light curves in ways that don't match any visible mass nearby. That opens up another possibility. Some of the cosmic voids, vast, empty regions between galactic clusters, might not be empty at all. They might be filled with negative mass, repelling ordinary matter and carving out giant bubbles of empty space. This could explain why matter in the universe clumps together the way it does, forming filaments and walls with nothing in between. The negative mass would act as a repelling force, keeping galaxies from spreading into those regions. And over billions of years, it would sculpt the large-scale structure of the cosmos into the strange sponge-like shape we see in modern sky surveys. But there's another twist. If negative mass exists, then it has its own version of gravity, and that means it might clump together, forming negative mass, galaxies, or even negative mass black holes. These would be invisible to our eyes, but not to their effects. A negative mass black hole would behave unlike anything we've ever seen. Instead of sucking in matter, it might repel it violently. Instead of collapsing light inward, it might scatter it. And in extreme cases, these objects could be mistaken for something else, like dark matter or even unexplained radiation sources. Now, remember those spacecraft anomalies? Some of the most controversial data in physics comes from deep space probes like Pioneer 10 and 11, which experienced unexplained accelerations as they traveled beyond the outer planets. These anomalies have mostly been explained by heat radiation, but not entirely. A few physicists have suggested that if the probes passed near a region of negative mass, they might have experienced a repulsive gravitational push. It would be subtle and hard to measure, exactly the kind of effect you'd expect if negative mass is rare and diffuse, like interstellar mist. Let's go back to theory for a second, because one thing keeps coming up over and over: the quantum vacuum. At the smallest scales, the universe is never truly empty. Even in the vacuum of space, there are quantum fluctuations, particles popping into and out of existence, borrowing energy from the vacuum, and then vanishing in pairs. Normally, these virtual particles come in particle-antiparticle pairs, balancing each other out. But some theories suggest that under certain conditions, like near a black hole, or in the early universe, those pairs might not balance perfectly. One side might have negative energy, the other positive. And if the negative energy side persists, you get negative mass. This connects to one of the most mind-blowing ideas in all of physics, the Casimir effect. It's a real, measurable force that comes from quantum vacuum fluctuations. When two metal plates are placed very close together in a vacuum, they experience a small attractive force, not from any ordinary force, but because the energy density between them is slightly lower than outside. Some researchers argue that this is a form of negative energy. If we could scale this up or control it, we might be able to create real negative mass effects in the lab. And we're getting closer. Experiments in quantum optics and condensed matter physics have already created effective negative mass in controlled systems. One study used supercooled atoms, a Bose-Einstein condensate, and manipulated them so that their motion mimicked negative mass behavior. When pushed, they accelerated backwards. This wasn't true negative mass in the general relativity sense, but it showed that under the right conditions, we can simulate these effects. It's like building a working model of a warp drive engine using magnets and water, not the real thing, but proof that the concept can exist. So what if negative mass is real? What if it's not just a curiosity, but a foundational part of the universe, something we've overlooked because it doesn't behave like normal matter? It would force us to rewrite everything. Not just general relativity, but quantum mechanics, cosmology, even the standard model of particle physics. It might unify gravity with quantum theory. It might explain why the universe started in the first place, a perfect symmetry broken at the Big Bang, with positive and negative mass expanding in opposite directions, creating the fabric of reality as we know it. And here's where it gets truly wild. What if we're only seeing one side of the universe? What if negative mass forms a mirror universe that exists alongside our own, invisible, untouchable, but gravitationally linked? Every galaxy we see might have a negative mass twin, repelling instead of attracting, warping spacetime in ways we can't directly observe. This mirror universe could explain so many of the mysteries we're still struggling with, from the nature of dark matter, to why time seems to flow in only one direction. Maybe entropy is just increasing in our positive mass universe, but decreasing in the negative one. And maybe, just maybe, we're on the edge of discovering how to reach it. Unexplained lensing anomalies where light from distant stars bends in ways that don't match what we'd expect from known gravitational sources. These could be early clues that negative mass objects or regions are lurking out there, subtly influencing the shape of the universe without being directly visible. Because remember, negative mass wouldn't emit light. It wouldn't reflect it. It wouldn't absorb it in the way normal matter does. It would be like a ghost, only interacting through gravity. That makes it incredibly hard to detect, but not impossible. One of the most compelling ideas is that some of the voids, we see in deep space, those vast, seemingly empty regions between galactic filaments, might not be empty at all. Instead, they might be filled with negative mass, repelling ordinary matter and shaping the cosmic web in a hidden tug-of-war. In fact, some simulations have shown that if you fill those voids with negative mass, the large-scale structure of the universe begins to match what we actually observe: the spacing of galaxies, the movement of clusters, the speed at which structures form. It starts making sense. But here's the part that's even more mind-bending. What if our entire understanding of space is biased because we only live in a positive mass region? Let that sink in. Everything we've ever observed, touched, measured, it's all made of positive mass. All our theories and physics laws are based on this assumption. But if there's a mirror reality out there, one dominated by negative mass, then the universe might be way stranger than we think. Imagine galaxies made of negative mass, repelling each other instead of attracting. Imagine black holes that don't pull things in, but spit things out. What if the laws of physics are different in those regions? What if light travels differently? Time flows differently? Or worse, what if there's no boundary between their universe and ours? That leads into one of the most unsettling possibilities, that negative mass regions could one day come into contact with our own. If they exist in vast clouds or voids, and if they drift or expand like other cosmic structures, then it's not impossible that our galaxy might one day encounter one. And if that happened, the effects could be catastrophic. Massive distortions in gravity, sudden reversals of motion, entire stars flung out of their orbits, time and light behaving in ways that make no sense. And we might not even see it coming. Because again, negative mass doesn't look like anything we know. It might be dark, silent, invisible. But gravity doesn't lie. If you see something moving in ways that defy Newton and Einstein, chances are there's something exotic at work. And we have seen things like that. There's a growing list of astronomical observations that just don't fit. Stars on the edges of galaxies moving too fast, the classic case for dark matter. But what if part of that motion isn't due to unseen positive mass holding them in, but due to unseen negative mass pushing them out? It's a completely different way of looking at the same data. Or take the mysterious, cold spot in the cosmic microwave background. It's huge, much colder than the rest of the universe, and nobody really knows why it exists. Some theories suggest it's the signature of a massive void, a region with very low density. But again, what if that's not just a lack of matter? What if it's the gravitational signature of negative mass bending light, distorting space, and creating the illusion of emptiness? Now let's turn things up a notch. There's one theory that goes even further, that negative mass isn't just floating around the universe. It's woven into the very structure of space-time. That every time and place is surrounded by a kind of negative energy sea. Invisible, undetectable directly, but critical for balancing the books of physics. In quantum field theory, we already know that empty space isn't really empty. It's buzzing with virtual particles, popping in and out of existence. This vacuum energy has measurable effects, like the Casimir effect, where two plates placed close together in a vacuum feel an attractive force due to energy differences between the inside and outside. But what if part of that vacuum energy is negative? What if it's negative mass trying to stabilize the quantum foam? That opens up a Pandora's box of implications. It would mean that negative mass isn't just possible, it's necessary. It could be the invisible skeleton of reality, holding everything together, balancing every equation, explaining the weirdness in quantum mechanics, even allowing for phenomena like entanglement and superposition to occur without violating basic conservation laws. And here's the scariest idea of all. If we ever learn to manipulate negative mass, truly control it, we wouldn't just be building warp drives. We wouldn't just be revolutionizing space travel. We'd be rewriting reality. Imagine building a device that creates a local region of negative energy density. You could, in theory, bend space, slow time, maybe even reverse entropy. That's not sci-fi. That's a natural conclusion from the equations. If you change the mass-energy content of a region of space-time, you change how time flows there. And if part of that mass is negative, you open the door to things like time machines, exotic wormholes, and other constructs we currently consider impossible. But nature has safeguards. Every time we've tried to build a system that uses negative mass in these extreme ways, we've hit walls. The energy requirements are massive. The stability problems are insane. Tiny fluctuations blow up into massive inconsistencies. It's almost like the universe doesn't want us to access this stuff. Like it's locked behind some kind of firewall we don't understand yet. Maybe for our own safety. Still, the theoretical door is open. And the more we explore deep space, the more anomalies we find, the more likely it becomes that negative mass isn't just an idea. It's real. It's out there. And one day, we might meet it face to face. Time and light behaving in ways we've never seen before. Clocks might run faster or slower depending on their distance from the negative mass field. Light might refract unpredictably, causing stars to vanish from view or appear displaced. In the worst-case scenario, entire systems could be torn apart, not by force, but by sheer incompatibility between the fundamental physics of our region and those of the negative mass domain. But before we dive deeper into those doomsday scenarios, let's take a step back and talk about something critical. How do we even begin to understand or detect negative mass? Physicists have proposed a few indirect ways. One of the most fascinating is through quantum field theory. In this framework, space isn't empty. It's buzzing with virtual particles popping in and out of existence, borrowing energy from the vacuum, and then disappearing again. Some theories suggest that under the right conditions, like intense electromagnetic fields or near certain exotic geometries, these quantum fluctuations could stabilize into regions of negative energy density. That's not quite the same as stable negative mass, but it's a hint. Then there's the Casimir effect, an observed quantum phenomenon where two uncharged plates placed very close together in a vacuum experience an attractive force. This happens because the energy density between the plates is slightly lower than outside, leading to a net push inward. That region between the plates is often described as having negative energy density. It's small, yes, but measurable. And it proves that negative energy isn't just theoretical. It can exist, at least temporarily, in our universe. That gives us hope that something much larger and more stable might also be possible. Now, if negative mass can exist, even in small quantities, then it opens a Pandora's box of implications for not just propulsion, but for shielding, cloaking, and even weaponry. Imagine using negative mass to create a gravitational lens that bends light around an object perfectly, rendering it invisible. That's not science fiction. That's gravitational lensing turned into a technology. Or imagine using negative mass fields to cancel out gravity in certain areas, making construction in space, or even on planetary surfaces, much easier. You could float structures without needing enormous supports. You could even cancel inertia, reducing the g-forces experienced during acceleration. But the most mind-bending implication of all might be this: what if negative mass is the missing piece to unifying general relativity and quantum mechanics? Right now, one of the biggest problems in physics is that Einstein's equations and quantum theory don't play nicely together. They each explain a part of the universe brilliantly: relativity for the cosmic scale, quantum theory for the subatomic. But trying to unify them has been like mixing oil and water. They just don't blend. However, some physicists believe that exotic matter, including negative mass, might act as a bridge between these two frameworks. In other words, negative mass might not just be a strange byproduct of the universe. It might be the glue that holds the deeper structure of reality together. Think about that. If it turns out that negative mass is real, then everything we thought we knew about the universe would have to be rewritten. Our models of cosmology, the Big Bang, the expansion of space, the fate of the universe, all of it would be up for re-evaluation. And perhaps most disturbingly, we'd have to face the fact that we are not living in a universe governed by a single, consistent set of rules, but in a fragmented reality where different regions follow different physical laws. And that raises a final, terrifying thought: what if intelligent life already exists in a negative mass region? We always assume that life, if it exists elsewhere, would be built on the same chemistry as us: carbon, water, proteins, and so on. But if entire regions of the universe are dominated by negative mass and exotic physics, then why wouldn't those regions also give rise to their own form of intelligent life? Beings made not of atoms, but of whatever structures emerge from negative mass interactions. They wouldn't interact with our light. They wouldn't reflect radio waves. They could be watching us right now, undetectable because their entire existence is incompatible with our sensors. And if they are truly intelligent, they might have already mastered negative mass technology, not just for propulsion, but for surveillance, manipulation, and travel. They could be moving through our universe using shortcuts we don't even know exist, slipping between positive and negative mass regions like fish navigating currents. And maybe, just maybe, they're not friendly. Not because they're evil, but because to them, we might be a threat, or a curiosity, or an obstacle, or maybe just irrelevant. What do you do when you encounter a colony of ants while building a house? You don't negotiate. You don't try to communicate. You just build over them. Is it possible that the same could happen to us, that one day, without warning, a negative mass civilization could collide with ours, not out of malice, but out of total indifference? That's the risk. That's the fear. That's the mystery. And yet, that's also the wonder. Because if negative mass is real, if these bizarre, reality-bending regions of the universe actually exist, then we are living in a cosmos far more strange, more beautiful, and more dangerous than we ever imagined. A cosmos where physics bends, where time warps, where matter flows backward, where alien life might be built from things we can't see. A universe not of empty space and scattered stars, but of hidden energies, unseen forces, and the possibility that everything we know is only half the truth. What if negative mass is the missing piece in our understanding of everything? Dark energy, dark matter, the rapid expansion of the universe, the strange behavior of galaxies, the inconsistencies in the standard model. For decades, we've been patching up our understanding of the cosmos with placeholders, invisible things we can't detect directly, but that we know must be out there because their gravitational fingerprints are unmistakable. But what if all those clues are pointing to a single answer we've been too afraid, or too unequipped, to accept? Negative mass could be that answer. Let's break this down even further. Right now, we believe dark energy is responsible for the accelerating expansion of the universe. But we don't know what it is. It's just a name for a force that pushes galaxies apart faster and faster as time goes on. But if large regions of space contain negative mass, and if negative mass repels both itself and positive mass, then it would naturally cause an accelerating expansion. It wouldn't be some mysterious, dark energy injected into the universe. It would be the gravitational consequence of a real, albeit strange, substance spread throughout the cosmos. And dark matter? That one's trickier, because dark matter pulls. It holds galaxies together when, by all accounts, they should be flying apart. But here's a twist: if negative mass exists in a kind of fluid form, it might flow around galaxies, forming halos. And its interaction with positive mass could be more complex than simple repulsion. In some theoretical models, negative mass could actually clump around positive mass in such a way that it amplifies gravity in the right places. It wouldn't just repel everything, it would move in weird, self-balancing ways that mimic the pull of dark matter. Now here's a thought experiment that'll keep you up at night. What if dark energy and dark matter aren't two separate things? What if they're just two sides of negative mass, behaving differently at different scales? When it's diffuse, it causes repulsion, dark energy. When it's concentrated near galaxies, it creates gravitational effects that mimic dark matter. That would mean everything we've been trying to solve for decades could collapse into one idea. One elegant, strange, reality-shattering idea. But the implications go even further than cosmology. Let's talk about time. Negative mass might allow for stable wormholes, bridges between points in space and time. One of the biggest issues with traversable wormholes is that they require something called exotic matter, with negative energy density to keep them open. Ordinary matter would collapse the throat of the wormhole under its own gravity. But negative mass? That could keep the tunnel propped open indefinitely. If we could harvest or manipulate negative mass, it wouldn't just be warp drives. It wouldn't just be invisibility. It could mean time travel. And I'm not exaggerating here. Some of the top physicists in the world have considered this seriously. Kip Thorne, a Nobel Prize winner, explored these ideas in the 1980s and 90s. His work showed that with enough negative energy, you could build a wormhole and even create a time machine, allowing information or even objects to travel backwards in time. Of course, there are 1,000 caveats, paradoxes, instabilities, energy requirements we can barely comprehend. But in principle, it's not impossible. Negative mass is the key to unlocking that door. Now think about that for a second. A substance that might exist in the fabric of space, in the voids between galaxies, could be the thing that connects distant corners of the universe, explains its shape and fate, and even opens the possibility of seeing the past or future. And yet, we've barely scratched the surface. We don't have the tools to directly observe it. We don't have the math to fully describe it. All we have is a collection of hints, scattered across disciplines: astronomy, particle physics, quantum mechanics, general relativity. And the weirdest part? Some scientists believe we may have already seen negative mass, and just didn't realize it. There was an experiment at the University of Rochester in 2017. They created a strange state of matter using ultra-cold rubidium atoms, a Bose-Einstein condensate, and applied a special laser technique that flipped the relationship between force and motion. When they pushed the atoms, they accelerated in the opposite direction. That's negative effective mass. It's not quite the same as cosmic negative mass, but it shows that under the right conditions, we can simulate this behavior in the lab. That's huge. It means the door to experimentation is cracked open. And once you can test it, you can understand it. Once you can understand it, you can control it. Now imagine the consequences of that. Imagine an era where negative mass isn't just a theory. It's a resource, a technology, a tool we use. The entire landscape of science and civilization would change overnight. We'd leave rockets behind. We'd bend space instead of crossing it. We'd lift cities without engines. We'd talk about distances in terms of warps, not miles. And time? Time might become a direction we choose to move in, not a prison we're trapped inside. But there's a price to pay for power like that. Because if we could harness negative mass, so could something else. What if negative mass isn't just a byproduct of physics? What if it's a clue to other forms of intelligence? Advanced civilizations, billions of years ahead of us, might not build spacecraft. They might not need planets. They might exist within the negative mass regions, immune to the gravitational constraints we face. Invisible to our sensors. Immune to light. Repelled by our matter, and possibly unaware of us. Or worse, fully aware of us, choosing to stay hidden. Think about it. If they're using negative mass to shape reality, to travel between stars, to compress time and stretch space, we wouldn't recognize it as technology. We wouldn't even see it. It would just look like anomalies. Void regions. Gravitational lensing we can't explain. Maybe some of those odd signals we've been picking up, those repeating fast radio bursts, those strange cosmic rays, maybe those aren't natural phenomena. Maybe they're side effects of a civilization engineering space itself. And maybe, just maybe, negative mass is their medium. We've spent centuries looking outward, thinking life and intelligence would appear as carbon-based organisms living on planets. But what if that's just a phase? What if the next step is abandoning matter altogether, and existing as fields of negative energy, spreading across space, evolving not through biology, but through manipulation of the very fabric of the cosmos? That might sound like science fiction. But every great discovery starts that way. Electricity, flight, quantum mechanics, black holes. Once laughed at, now foundational. Negative mass might be next. And we're only beginning to understand what that really means. And that's where things get seriously wild. In theory, a wormhole, a tunnel through space and time, could allow you to travel from one point in the universe to another instantly. But there's a catch. Wormholes are inherently unstable. The moment you try to send something through them, they collapse. That's where negative mass comes in. According to general relativity, negative mass could provide the exotic matter necessary to hold the wormhole open. It would act like scaffolding around the mouth of the tunnel, preventing it from collapsing under its own gravity. And if that's true, if negative mass can stabilize wormholes, then time travel may no longer be a fantasy. Here's how it might work. Suppose you have two ends of a wormhole. You accelerate one end close to the speed of light and then bring it back. Due to time dilation, one of the most bizarre effects of Einstein's relativity, time moves slower for the traveling end. When you reconnect the two ends, they're now out of sync. Travel through the wormhole from one end to the other, and you've effectively moved through time. You've gone into the past. This doesn't just violate what we thought was possible. It obliterates it. Of course, this leads to all the paradoxes. The grandfather paradox, causality loops, alternate timelines, the stuff of sci-fi. But here's the thing, if negative mass exists, then the mechanics of time travel move from impossible to extremely difficult, but maybe possible. And that alone should shake you. But even if time travel never becomes practical, the idea that negative mass could allow us to manipulate the very fabric of space and time is revolutionary. Imagine what this means for computing, for communication, for observation. If you can bend space, you can send signals faster than light by hopping through shortcut paths in spacetime. That breaks every limit we've ever assumed was unbreakable. It means interstellar communication isn't just a dream, it's a real possibility. Now, let's take a breath and think about this from another angle. Where would negative mass come from? Is it a natural part of the universe, hiding in the corners we haven't explored yet? Could it exist deep in black holes, or just outside them in regions of extreme curvature? Could it be floating between galaxies, masquerading as empty space? Or, and here's a brain melter, could it have been created? This brings us to an unsettling idea. What if negative mass isn't a relic of the Big Bang, but something that can be generated? Some speculative theories in quantum field dynamics suggest that, under certain vacuum conditions, it might be possible to trigger the formation of negative energy particles. If we can isolate and stabilize them, that's the first step to engineering artificial negative mass. That would mean we're not just discovering the secrets of the cosmos, we're beginning to rewrite the rules of the universe itself. And here's where things spiral into pure, next-level territory. What if there are entire regions of the universe, massive cosmic zones, where negative mass dominates? In our observable bubble, positive mass rules. But beyond our cosmic horizon, maybe the rules are flipped. Maybe somewhere out there, negative mass stars are burning in a negative mass galaxy, orbiting a negative mass black hole, within a universe that repels ours. A universe we'll never reach, because the closer we get to it, the more it pushes away. And yet, perhaps the border between these two regions, ours and the negative one, is exactly what's driving cosmic acceleration. Not some weird force within our own universe, but a cosmic pressure caused by a universe made of negative mass, pushing ours outward like two balloons pressed together, slowly drifting apart. Here's a question that should send chills down your spine. What happens if those two universes touch? What happens if a negative mass region collides with ours? Would it cancel out matter like matter and antimatter do? Would it tear open a rift in the fabric of reality? Would it simply bounce off and continue on its way, leaving a trail of warp space in its wake? We don't know. But we might find out, sooner than we think. Because more and more astronomers are seeing strange anomalies in the sky. Regions where galaxies behave oddly. Areas where expansion is faster than expected. Places where gravitational lensing doesn't match the visible mass. We used to assume it was just dark matter, or dark energy, or errors in measurement. But now, some scientists are whispering another possibility. Maybe we're looking at the edge of something foreign. maybe we're peering into a place where the universe has already started to change. And if that's true, we might not have a choice. We might have to understand negative mass fast. Nothing. Simply because our instruments can't detect it directly? Or, and this is even more mind-bending, could it have been created in the earliest moments after the Big Bang, alongside positive mass, as part of some perfect cosmic balance we've yet to fully understand? Let's dive into that. Imagine the instant after the Big Bang. The universe was unimaginably hot, dense, and chaotic. Particles and antiparticles were popping in and out of existence. Space-time itself was stretching and rippling in ways we can barely comprehend. In that frenzy, could positive and negative mass have formed together? Not like matter and antimatter, which cancel each other out, but like two gravitational opposites. Positive mass clumps, attracts, and forms stars and galaxies. Negative mass spreads out, repels, and maybe forms the cosmic web that supports everything else. If negative mass was created at the same time as positive mass, why does the universe seem dominated by positive mass today? One idea is that negative mass repels itself, so it naturally spread out much more quickly after the Big Bang. It didn't clump into stars or planets, it escaped, flowing into the vast voids between galaxies, into the unseen scaffolding of the universe. It could be everywhere, hiding in plain sight, impossible to detect by ordinary means but always exerting its strange gravitational influence. And this isn't just theory for theory's sake. Physicists have actually started modeling entire universes that include negative mass. In those models, galaxies behave more like what we observe in reality, with their rotation curves matching what we see through telescopes. Cosmic expansion accelerates without any need for dark energy. The large-scale structure of the universe, with its dense filaments of matter surrounding vast empty voids, starts to make more sense. The need for two separate unexplained forces, dark matter and dark energy, vanishes. And in its place, we get a single, elegant idea that fits everything. But there's a problem. If negative mass is so useful in theory, why haven't we found it? Why haven't we detected even a single particle of it? That's where things get tricky, and where our understanding of physics may still be too primitive. Negative mass doesn't behave like anything we've ever seen. It repels when pushed. It might move in bizarre feedback loops. It might not interact with light or ordinary matter in any measurable way. It could be like a ghost, present, influential, and totally untouchable with our current tools. Worse yet, it might actually avoid detection on purpose. Let me explain what that means. Because of its repulsive nature, negative mass could push itself away from regions where there's a lot of positive mass, like our solar system, or even our entire galaxy. That would leave it drifting in the deepest parts of intergalactic space, far beyond the reach of even our most powerful telescopes. Our searches for dark matter often focus on gravitational lensing, how mass bends light around it, but negative mass might bend light in the opposite way, making it harder to spot. It might even unlens light, decreasing its brightness, distorting it in ways we don't yet recognize. So our instruments could be staring directly at it, misinterpreting the data because the signatures don't match anything we expect. But what if we have seen it, we just didn't know what we were looking at? Some cosmologists have pointed out that the vast empty voids between galaxy clusters are too empty. They're darker, colder, and more uniform than standard models predict. And the galaxies that do sit around these voids often move in strange ways, as if they're being pushed. Traditional physics says these motions are anomalies. But if you plug negative mass into the equations, even in small amounts, the behavior starts to make sense. So now the question becomes, can we create it? That's where things get even more intense. In high-energy physics, there have been attempts to simulate what negative mass might look like under controlled conditions. Some researchers have used supercooled atoms, specifically Bose-Einstein condensates, to create systems where particles behave as if they have negative mass. In one famous experiment, physicists manipulated rubidium atoms with lasers in such a way that, when pushed, they accelerated in the opposite direction. In other words, they didn't actually have negative mass, but they followed the same rules. It was a breakthrough. Not because it proved negative mass exists, but because it showed that the behavior is possible, and perhaps not as exotic as we once believed. If we can scale up these experiments, and if we can find a way to stabilize systems with this strange behavior, we might eventually figure out how to engineer negative mass. And if we do that, the door swings wide open, not just for understanding the universe, but for changing it. Imagine spacecraft that don't need fuel. If negative mass repels positive mass, then by pairing equal amounts of both, you could create a propulsion system that pushes itself forever, a runaway drive that accelerates endlessly without burning a single drop of fuel. Science fiction? Maybe. But the math checks out. Or consider artificial gravity. By carefully placing negative mass in specific configurations, you could simulate the pull of Earth's gravity without any massive object nearby. It could revolutionize space stations, colonization, and even long-term life in orbit. But maybe the most dramatic possibility is the manipulation of spacetime itself. With negative mass, you could, in theory, bend space like never before. Warp drives, like the Alcubierre drive, require negative energy to expand space behind a ship and contract it in front. That would allow faster-than-light travel without violating relativity, because the ship itself wouldn't be moving faster than light, space around it would. But the catch has always been energy. The Alcubierre drive requires negative energy densities so massive that it's always seemed impossible. But if negative mass is real and abundant, then maybe it's not. Suddenly, the stars don't seem so far away. But let's be real. We're not there yet. We're still in the stage of mapping shadows on the cave wall, trying to make sense of movements we can't fully see. But the shadows are starting to take shape. And every time we look a little deeper, every time we stretch our theories a little further, the idea of negative mass keeps reappearing, persistent, consistent, and maybe even inevitable. So where do we go from here? We build better detectors. We develop better models. We reanalyze the data we already have with new eyes. Because maybe the next great discovery won't come from a new telescope, but from a new way of thinking. Maybe we've been looking for the wrong thing in the wrong way. And maybe, just maybe, the answer has been right in front of us all along. Light in any way we currently know how to measure. That means it could literally be invisible, not in a cloaking device kind of way, but in the sense that our most sensitive detectors, built to interact with photons and electromagnetic fields, would just pass right through it without noticing a thing. It's like trying to find air with a net made of holes too big to catch it. Some scientists believe that what we call dark energy, the mysterious force accelerating the expansion of the universe, might actually be a large-scale manifestation of negative mass. Think about it. The galaxies aren't just drifting apart slowly. They're accelerating away from each other. That goes completely against gravity as we've known it. But if negative mass exists in large quantities in the empty spaces between galaxies, then that repulsive force might explain the acceleration. Instead of needing a whole new form of energy to stretch the universe, we might just be misinterpreting the effect of negative mass repulsion. Now let's get into the weeds a bit, because the math behind this is where it starts to feel almost magical. In Einstein's field equations, the core equations of general relativity, mass and energy determine how space-time bends. But the equations themselves don't strictly forbid negative mass. In fact, if you plug in a negative value for mass, the math still works. The geometry of space-time still warps, just in the opposite direction. Instead of creating gravity wells that pull matter in, you get gravity hills that push matter away. And this leads to a fascinating idea. What if the universe isn't just filled with invisible negative mass particles, but also negative mass structures? Imagine a massive cloud of negative mass drifting across the void. It wouldn't clump like regular matter, but it might create gravitational anomalies. A spacecraft passing nearby would experience unexpected forces. Its trajectory would bend, not toward the object, but away from it. And if we're not accounting for negative mass in our models, we'd look at that and just assume our instruments are malfunctioning, when in fact, they might be detecting something revolutionary. There's even been speculation that some of the weirdest anomalies we've seen in space, like the flyby anomaly, where spacecraft gain unexpected amounts of speed during planetary flybys, could be the result of passing near regions of concentrated negative mass. These are just theories, sure, but they point to one critical fact. The more we look at the universe, the more cracks we find in the traditional model. Let's talk now about the Alcubierre drive, a concept that feels ripped straight out of science fiction but is grounded in real physics. In 1994, physicist Miguel Alcubierre proposed a warp drive concept based on general relativity. It wouldn't move a ship through space in the usual sense. Instead, it would compress space in front of the ship and expand it behind, effectively pushing the ship forward without it ever technically moving faster than light. The catch? You'd need negative energy, or negative mass, to make it work. That's because the Alcubierre metric requires what's called exotic matter, with negative energy density to shape spacetime in the needed way. Positive mass couldn't do it. It would collapse the warp bubble instead of stabilizing it. So once again, the key to a faster-than-light future hinges on whether or not negative mass actually exists. And get this, some physicists think that quantum mechanics might actually allow for negative energy, at least in tiny amounts. In certain quantum field configurations, such as the Casimir effect, energy densities can drop below zero. These aren't quite the same as large-scale negative mass, but they suggest the idea isn't totally outside the bounds of physical law. It's just, really hard to get enough of it in one place to do anything useful. But suppose we did. Suppose we learned how to manipulate negative mass, maybe by mining it from regions of deep space, or creating it using high-energy particle collisions, or even engineering it from vacuum fluctuations in a lab. Suddenly, the universe becomes a much smaller place. Travel to distant stars, currently a fantasy requiring thousands of years, becomes a real possibility. Colonizing planets around Alpha Centauri or Proxima b doesn't seem so far-fetched. And more than that, if we could generate enough negative mass to stabilize a wormhole, we wouldn't just be traveling fast. We'd be bypassing distance entirely. You could walk into a chamber on Earth and step out onto the surface of a planet light years away. Or into a future version of Earth. Or into the past. It's the ultimate escape from the limits of time and space. But before we go all in on dreams of interstellar road trips and time machines, there's another possibility we need to talk about, one that's even darker. What if negative mass is already influencing us, and not in a good way? There's a controversial theory that some black holes, specifically rotating ones, could contain regions of negative mass at their cores. These aren't your typical black holes that just suck everything in. These are hypothetical monsters that might twist space and time so violently, they spew out jets of energy, antimatter, or even chunks of distorted spacetime. Some physicists think negative mass might be involved in that process. And if that's true, then every time we observe a black hole flaring up or ejecting something from its poles, we might be watching negative mass in action. Not theoretical. Not distant. Not someday. But here, now, tearing at the edges of reality. And that raises an even more unsettling thought. If negative mass is real, and if it can repel everything around it, then it might be the reason we haven't found advanced alien civilizations. Think about it. If a civilization figured out how to weaponize negative mass, they'd have a way to create barriers in space that couldn't be crossed. A kind of gravitational firewall. An impenetrable wall of repulsion. They could use it to cloak entire star systems, or push away incoming threats, or even seal off regions of space permanently. That would make them invisible to us, and make us irrelevant to them. They wouldn't need to attack or explore or even communicate. They'd just isolate themselves forever behind walls of gravity we can't penetrate. Or maybe they tried to use negative mass, and failed. Maybe they tore holes in reality that couldn't be repaired. Maybe they created runaway effects, negative mass bubbles that grew exponentially, and devoured everything. Maybe that's the real reason the universe is so quiet. We look out and see nothing. But maybe that's because something was here before us, and now it's gone. But they're not as far out as they might sound. The thing about science is that every major discovery starts as something strange, something that doesn't quite fit. Newton couldn't explain why Mercury's orbit didn't match his predictions. Einstein's theories did. Then came the discovery that galaxies were rotating in a way that made no sense. Their outer stars were moving too fast, like they were being held together by invisible mass. That gave rise to the idea of dark matter. And when we noticed that galaxies were flying apart faster and faster, not slower, that gave rise to dark energy. But what if both those mysteries, which we've treated as two separate problems for decades, are actually just one? What if negative mass has been the missing puzzle piece all along? Now here's where things get even more mind-bending. Some physicists have proposed that if you had a negative mass and a positive mass close together, they could create what's called a runaway motion, a system where both objects accelerate in the same direction forever. That doesn't sound possible at first, but it's actually allowed by the math. The positive mass is attracted to the negative mass, and the negative mass is repelled by the positive mass. Put them together, and they move together, faster and faster, without needing any additional energy. It's like creating an engine that powers itself, which would break everything we know about thermodynamics. Except it might not be breaking the rules. It might be that we've misunderstood the rules. Maybe the universe has loopholes that only open up when negative mass is involved. This leads to some pretty wild implications. If negative mass exists and can interact with positive mass like this, then we might be able to use it to build propulsion systems that don't need fuel. Imagine a spacecraft with a small amount of negative mass paired with a small amount of positive mass, constantly accelerating through space without burning anything. That could revolutionize space travel. It could get us to other star systems in a fraction of the time we'd expect. Some theories even suggest that negative mass could allow for the creation of stable wormholes. That's right, actual shortcuts through space-time. According to general relativity, wormholes are possible, but they would collapse instantly unless they're held open by something that creates negative energy density, something just like negative mass. If we could find or generate even a small amount of it, we might be able to stabilize a wormhole and step across the galaxy in an instant. Now, don't get too excited, none of this has been proven yet. But here's where it gets interesting again. While we haven't directly detected negative mass, we've created something like it in the lab. In 2017, physicists at Washington State University created a fluid of supercooled rubidium atoms, a Bose-Einstein condensate, that behaved just like negative mass under certain conditions. When they pushed it, instead of moving in the direction of the push, it moved in the opposite direction. That's exactly what negative mass is predicted to do. It wasn't true negative mass, but it was the first time we'd seen that kind of behavior in any physical system. That experiment didn't get much attention outside the physics community, but it was a massive step forward. It showed that the concept isn't just theoretical, it can be modeled, tested, and maybe even engineered. Now think about this. If we can simulate negative mass in the lab, even in a limited way, then maybe we can learn to manipulate it. And if we can manipulate it, maybe we can build devices that use it. Gravity shields, warp drives, even artificial gravity for spacecraft. All these science fiction dreams suddenly start to look just a little more realistic when negative mass enters the equation. But it's not just about spaceships and wormholes. Understanding negative mass could unlock the next level of cosmology. For instance, it could help explain why the universe looks so flat. The cosmic microwave background, that faint glow from the early universe, suggests the universe is balanced on a knife edge between open and closed. That's incredibly unlikely unless something is balancing the equation. Could negative mass be the counterweight that keeps everything in cosmic equilibrium? It might also help solve the puzzle of cosmic inflation, the period right after the Big Bang when the universe expanded faster than the speed of light. That expansion required some kind of repulsive force far stronger than anything we know today. If negative mass was present at the time, it might explain how the universe ballooned outward in an instant. And if pockets of it still exist today, maybe they're still pushing outward, driving the expansion we see all around us. Let's go even further. Some theories suggest that negative mass could lead to the creation of entire pocket universes, baby universes that split off from our own. In quantum field theory, energy fluctuations can create tiny bubbles of space-time. Normally these bubbles collapse immediately. But if one of them contains enough negative energy, it might not collapse. It might expand, forming its own universe with its own physical laws. Could our universe be one of those bubbles? Could there be others, formed by some strange balance of positive and negative mass in the quantum foam? We might never know for sure. But the idea that our entire reality, space, time, gravity, matter, might be shaped by a kind of mass we've never seen before, but which fits all the gaps in our models, that's hard to ignore. It means we're still at the very beginning of understanding the cosmos. It means that all our physics, all our theories, all our assumptions might be just a tiny piece of a much bigger picture. And maybe, just maybe, we're finally starting to see the edges of that picture. A tiny bit of real, stable negative mass, it might be the key to unlocking traversable wormholes, not the kind that exist for a billionth of a second, but ones that could stay open long enough to allow something, or someone, to pass through. Think about that for a second. We're not just talking about faster space travel anymore. We're talking about the potential for instant travel between galaxies, or even between different regions of the universe that would normally be separated by billions of light years. It's a concept that sounds like pure science fiction, but it's actually rooted in serious theoretical physics. Now, here's where things get even stranger. Some models of the early universe, the first few fractions of a second after the Big Bang, suggest that negative mass might not just exist, but might have actually played a role in shaping the cosmos as we know it. In some inflationary models, regions of space with different mass properties could have expanded at different rates. Areas dominated by negative mass could have inflated too quickly, essentially becoming unreachable from our part of the universe. They could still be out there, infinite stretches of space completely made of negative mass, separated from us by unreachable horizons. And yet, even if we can't see them, the gravitational influence of those regions might still affect the large-scale structure of our universe. This also ties into the concept of voids in space, enormous, dark regions where almost no galaxies exist. Astronomers have mapped the universe in 3 dimensions and found not just clusters of galaxies, but also giant, empty bubbles. Some of these voids are so vast and so empty that they can't easily be explained by the normal distribution of matter. What if those voids aren't empty, but full of something we can't see, like negative mass? That could explain why light bends around them in unexpected ways, or why galaxies at the edges of these voids seem to be pushed outward, as if repelled by some invisible force. And here's another mystery that might make more sense if negative mass exists: the cosmological constant problem. This is one of the biggest unsolved issues in physics. When we calculate how much energy should be in empty space, based on quantum field theory, we get a number that's 10 superscript 1 superscript 2 times too big. That's a number so insanely huge, it's hard to even describe. It's like predicting a single coin will weigh more than the entire observable universe. But what if some of that energy is being cancelled out by negative mass contributions? What if the vacuum energy is balanced, not by accident, but because there's an invisible, negative component that offsets the positive one? That could bring our equations back in line with what we actually observe. Even more bizarrely, negative mass might help explain dark matter, too. Right now, dark matter is one of the biggest mysteries in cosmology. We know it's there, we can see its gravitational effects, but we've never been able to detect it directly. We've spent decades trying to find particles that could make up dark matter, but so far, nothing's shown up. But if there's a halo of negative mass surrounding every galaxy, pushing inward while positive mass pushes outward, that could stabilize galaxy rotation in the same way dark matter is supposed to. Some researchers have even run computer simulations where they replace dark matter with negative mass, and they find that the galaxies still form and behave in realistic ways. It doesn't prove that negative mass is real, but it's a big clue that we might be looking at the problem from the wrong angle. And then there's the possibility, a little unsettling, that we've already detected negative mass, But we just didn't know it. In 2018, physicists at Washington State University announced that they had created a fluid with negative mass in the lab. They used ultra-cold rubidium atoms, chilled to just above absolute zero, and manipulated them with lasers. When they pushed the fluid, it accelerated backwards, exactly as negative mass is supposed to. Now, this wasn't true negative mass in the sense of a fundamental particle with a negative gravitational effect. But it was a step in that direction, a material system that behaves like negative mass under certain conditions. It's a demonstration that the physics is real, and it opens up the possibility that maybe negative mass isn't just some abstract concept. Maybe it's something we can create and control. So what does this all mean? It means we're standing on the edge of a massive unknown. Negative mass isn't just some weird theory, it's a possible key to solving multiple, seemingly disconnected mysteries in physics. It could explain dark energy. It might replace or supplement dark matter. It could open up entirely new kinds of propulsion. It could stabilize wormholes. It might help us understand the origin and fate of the universe. But here's the kicker. If negative mass exists, then it's very likely that the universe is far stranger than we ever imagined. We're talking about a cosmos where entire regions might be made of reversed matter that we can't see or touch, but which silently shapes the structure of everything. A universe where space isn't just expanding, but accelerating because of a repulsive, invisible pressure between the stars. A universe where light bends in strange ways, not just because of massive galaxies, but because of hidden gravitational hills made of negative mass. And if we keep exploring, keep refining our instruments, keep asking uncomfortable questions, we might finally be able to see what's been hiding in the dark this whole time. Not just a new kind of particle. Not just a tweak to our equations. But a whole new side of reality that turns everything we thought we knew upside down. It would rain every single drop of water in all the oceans on Earth, every second, for 1 billion years straight, and still being off by a factor of 10,000. That's how wrong our calculations are when it comes to the cosmological constant. This discrepancy is not a minor error. It's one of the most extreme mismatches between theory and observation in all of science. But what if the solution is that we're only seeing part of the picture? What if the universe's vacuum energy, the energy of empty space, is being balanced out by something we're not accounting for? Something like negative mass. See, negative mass could act as a kind of cosmic counterweight, canceling out the absurdly high vacuum energy that quantum mechanics predicts. If positive vacuum energy pushes space to expand faster, maybe negative mass energy pulls it back just enough to get the universe expanding at the rate we actually observe. Instead of trying to fix the equations or add new forces, this theory says, maybe the universe is fine as it is. We just haven't factored in everything that's there. And if that's true, then it's not just the voids in space, or the shape of galaxies, or the speed of expansion that negative mass helps explain. It's the very stability of the universe itself. The balance between all these forces might depend on the presence of both positive and negative mass, like a cosmic yin and yang. Without one, the other might fly out of control. Now let's take a moment to appreciate how deep this rabbit hole really goes. If negative mass regions exist, and if they obey the strange laws predicted by physics, then we're dealing with matter that does the opposite of everything we know. It doesn't just act weird, it breaks our intuition at every level. Push it, and it comes toward you. Gravity pulls on it, and it accelerates the other way. Try to trap it in a container, and it pushes through walls, not because it's magic, but because the laws of motion flip when mass is negative. In some scenarios, it could even cause paradoxes, or lead to the breakdown of causality, where effects happen before causes. That would shatter our understanding of time itself. And it gets even wilder. In quantum theory, particles constantly pop in and out of existence in what's called the vacuum fluctuation. These pairs, a particle and an antiparticle, exist for a tiny fraction of a second before annihilating each other. But some physicists have speculated, what if these pairs aren't always just particle-antiparticle? What if sometimes they're particle, negative mass particle? That would change everything about quantum field theory. It would mean the vacuum isn't just full of fleeting energy. It's full of exotic mass that could influence the universe in subtle but massive ways. And think about this. If we could tap into those negative mass fluctuations, even indirectly, we might learn how to control space itself. It could open the door to things we've only dreamed of: artificial gravity, inertial dampening, warp drives, even time manipulation. These aren't just dreams from sci-fi movies. They are actual predictions that fall out of the equations when negative mass is plugged in. Of course, the big question is, does it exist? That's the million-dollar problem. So far, we haven't directly observed negative mass. No one's captured a clump of it in a lab, and no telescope has zoomed in on a galaxy made entirely of repelling matter. But here's the thing, maybe we're looking for the wrong thing. Negative mass wouldn't show up like regular matter. It wouldn't emit light. It wouldn't absorb it either. In fact, it might deflect light in the opposite way that regular mass does, creating gravitational lensing effects that mimic the patterns we already attribute to dark matter. So when astronomers spot galaxies that seem to be held together by invisible hands, maybe those hands aren't made of dark matter. Maybe they're made of negative mass, just hiding in plain sight. And that's not just speculation. In 2017, a theoretical physicist named Jamie Farnes from Oxford proposed a unified theory where negative mass could explain both dark matter and dark energy, the two biggest mysteries in modern cosmology. He ran computer simulations showing how a universe filled with negative mass could form structures that look like what we actually see. Galaxies still form. Clusters still spin. But the invisible glue holding it all together isn't dark matter, it's negative mass. Now, not everyone agrees with this. Some physicists argue that negative mass would be too unstable, that it would blow apart any normal matter it touches, or that it violates basic conservation laws. But others point out that we've accepted far weirder things in physics before, like quantum tunneling, or entanglement, or particles being in two places at once. Compared to that, negative mass isn't even the strangest idea on the table. And even if we never find a chunk of negative mass in a lab, we might still prove it exists by its effects. After all, we've never seen a black hole directly, we've only seen what it does to things around it. The same could be true of negative mass. We might confirm it not by touching it, but by understanding how it shapes the universe at the largest scales. So where does this leave us? We're left with a huge cosmic question mark. A possibility that sits at the edge of science, not proven, but not ruled out either. A possibility that could change how we understand space, time, mass, energy, and the fate of the entire universe. And we're just getting started. Appear out of nothing, exist for a tiny fraction of a second, and then annihilate each other, disappearing again. This happens constantly, everywhere in space. But what if, once in a while, instead of creating a particle and an antiparticle, which both have positive mass, the universe accidentally spits out a particle with positive mass and one with negative mass? Now, normally, this would still balance out. But if something interferes, maybe a powerful gravitational field, maybe an extreme environment near a black hole, that pair could be separated before they cancel each other out. The positive mass particle might get sucked into the black hole while the negative mass one gets flung out into space. What you're left with is a region of space that's slowly accumulating these exotic, negative mass particles, an invisible, undetectable soup that's warping the rules of physics in subtle ways. It's almost like there's an invisible layer to reality that we've barely begun to detect. We've mapped stars and galaxies. We've measured background radiation from the Big Bang. But what we haven't really measured is the truly empty space, the kind that might be harboring negative mass. Because if these particles are out there, they don't emit light. They don't reflect light. They don't interact with normal matter in the usual way. The only way we know they're there is by how they push and pull things around them, in ways that don't make any normal sense. And that might already be happening. Some galaxies rotate in ways that don't line up with the visible matter inside them. Their outer edges are moving too fast, as if being tugged by something unseen. Dark matter is one explanation. But negative mass could be another. A halo of invisible, Negative mass around a galaxy wouldn't pull things inward like dark matter would. It might push back just enough to balance the forces and still explain those strange rotations. And here's the kicker. In some computer simulations, when researchers introduced negative mass particles randomly into the early universe, the structures that formed looked shockingly like the universe we actually observe today. Webs of galaxies connected by filaments, separated by huge voids. The same cosmic patterns we see through our telescopes. So maybe what we're seeing out there, all those dark, empty regions between galaxy clusters, isn't just emptiness. Maybe it's nothing at all. Maybe it's the signature of something much weirder. Something that bends the rules, flips gravity, and hides in plain sight. Something the universe created alongside everything else, but that we've never fully grasped. And if that's true, then the implications are massive. It means we might be surrounded by negative mass right now and never even know it. It means the universe could be far less stable than we think. Or, and this is the scary part, it could mean that if negative mass interacts the wrong way with normal matter, it could cause runaway effects. Imagine a piece of negative mass coming into contact with something like a star. As the star's gravity pulls on the negative mass repels it, but accelerates back toward the star. The star keeps pulling, the mass keeps pushing, and the whole thing spirals into chaos. Energy gets pulled out of nowhere. Temperatures spike. Particles fly apart. The laws of thermodynamics break down. It's not just a cosmic disaster, it's physics itself unraveling. Some theorists even wonder if this kind of runaway interaction could explain the sudden appearance of quasars or gamma ray bursts, those ridiculously powerful events that seem to come out of nowhere. Maybe, just maybe, they're not just collapsing stars or feeding black holes. Maybe they're the visible scars of invisible physics, places where positive and negative mass clashed, and the universe screamed. Of course, all of this is still just theory. We haven't detected negative mass directly. We haven't built an experiment that proves it's real. But that doesn't mean we're not trying. Some researchers are working on ultra-sensitive gravitational sensors that might one day pick up the tiny push of negative mass particles. Others are looking into high-energy collisions and particle accelerators, searching for anomalies, patterns that don't fit, particles that behave strangely, signatures that hint at something truly exotic hiding just beyond the veil of normal matter. And that's the beauty of this mystery. It's not just about what's out there in the far reaches of space. It's also about what's right here, all around us. Negative mass might not be some distant curiosity. It might be part of the fabric of reality itself, part of the reason why our universe is still expanding, still alive, still full of unexplained patterns and questions. And the more we look, the more it seems like we're on the edge of discovering something that could change not just physics, but our entire understanding of existence. Maybe those dark voids are filled with something real, something fundamental, something that changes how everything in the universe behaves, even though we can't see it directly. Think about that. The most dominant ingredient in the structure of the cosmos might be completely invisible, not because it's far away or hidden behind dust or clouds, but because it literally repels our attempts to detect it. Every instrument we've ever built, every telescope, every probe, every particle accelerator, they're all designed to detect things that behave like regular matter. But if negative mass behaves in the exact opposite way, then those tools would all fail by design. They wouldn't just miss it, they'd be blind to it on a fundamental level. Now imagine building a new kind of detector. Not one that tries to see light, or measure gravity in the traditional way, but one that looks for disruptions in inertia. One that can detect if something speeds up when it's pushed, or, in the case of negative mass, if it speeds up in the opposite direction. That sounds impossible, but researchers are starting to theorize ways to test for these effects. Maybe in quantum experiments. Maybe in ultra-sensitive gravitational wave detectors. Or maybe in space itself, using the vast vacuum as a kind of giant laboratory. And speaking of laboratories, there's another twist. In 2017, physicists at Washington State University created something in the lab that behaves like it has negative mass. Not actual negative mass particles, but a state of matter called a Bose-Einstein condensate. They cooled rubidium atoms down to just a few billionths of a degree above absolute zero, creating a quantum fluid. Then they manipulated it so that, when pushed, parts of the fluid accelerated backwards, exactly how negative mass is supposed to behave. Now, that doesn't prove negative mass exists in nature, but it shows that the concept isn't just science fiction. It can be modeled. It can be tested. And maybe, just maybe, it's real. Because if we can recreate the behavior of negative mass in a lab, then nature, which is infinitely more complex, powerful, and ancient than anything we can build, could absolutely have done it too, on a massive scale, over billions of years. So let's say these regions of negative mass exist. Let's say they're real. What would that mean for everything else? Well, first, it might help solve the mystery of dark energy, the force that's accelerating the expansion of the universe. Right now, dark energy is a placeholder name for something we don't understand. But what if it's not some mysterious fifth force or constant pressure from the vacuum? What if it's just the effect of negative mass on cosmic scales? If negative mass pushes against positive mass, and there's enough of it spread out across the universe, it could create a repulsive effect on a galactic scale, a kind of built-in, cosmic anti-gravity. That would mean dark energy isn't a force at all. It's just geometry. It's just how different types of mass interact across space. And that's not just a cool idea. It could be the key to unlocking a unified theory of the universe. Because right now, our understanding of physics is broken into two massive, brilliant, and incompatible chunks. On one side, there's general relativity, Einstein's theory of gravity, space, and time. It explains how planets move, how stars bend light, how black holes form. But it doesn't work on the smallest scales. That's where quantum mechanics comes in, the physics of the very small, of particles, atoms, and forces. It's accurate to absurd levels, but it can't explain gravity. The two theories speak different languages. They've resisted unification for over 100 years. But maybe, just maybe, negative mass is the bridge. Maybe it's the missing piece of the puzzle. Because when you add it into the equations of both quantum physics and general relativity, things start to align. Some of the infinities that break the math in quantum gravity disappear. Some of the weird behavior in early universe models starts to make sense. It might not be the full answer, but it's a huge step toward connecting the dots between the very big and the very small. And if we go even deeper, to the far edge of physics, where time begins to unravel and space folds in on itself, we find theories that take negative mass even further. Some researchers believe it could be the foundation of exotic matter, the kind needed to create stable wormholes or warp drives. According to general relativity, it's theoretically possible to bend space so much that two distant points become connected, or to compress space in front of a spacecraft while expanding it behind, moving faster than light without violating the laws of physics. But to do it, you need negative energy. You need something that pushes instead of pulls. You need negative mass. That's why some of the most ambitious ideas in science fiction, teleportation, faster-than-light travel, time machines, aren't just dreams. They're equations. They're sketches in the margins of real physics papers. And while we're nowhere near building these things, we are inching closer to understanding the materials that would make them possible. But there's a darker side too. If negative mass can bend reality in such extreme ways, then it might also open doors we're not ready for. Some models suggest that regions filled with negative mass could create unstable bubbles, pockets of space where time flows backward, or where physical laws break down. If one of these bubbles formed near us, it could tear apart atoms, shred molecules, collapse stars. Not out of malice, but because the rules of space itself would be rewritten inside. Now luckily, there's no evidence of these destructive effects happening. But we're still just scratching the surface. The universe is 13.8 billion years old. Our instruments have only been around for a tiny sliver of that. Who knows what's happened in the past, or what's waiting out there now? And this brings us back to the biggest mystery of all. Why does the universe exist the way it does? Why is there something instead of nothing? Why are the laws of physics tuned just right to allow galaxies, stars, life, and consciousness to emerge? Negative mass might not answer all those questions, but it opens a new way of looking at them. Instead of seeing the universe as a machine made of parts, matter, energy, space, time, maybe we need to see it as a balance. A dynamic equilibrium between opposites. Not just light and dark, or matter and antimatter, but mass and negative mass. Maybe the void isn't empty. Maybe the silence of space is full of voices we can't yet hear. And maybe, just maybe, the reason we're here at all is because of that balance. Because the universe allows both sides to exist, even when we don't understand them. Completely rewrite our understanding of gravity. We've always assumed that mass attracts mass, that everything with mass pulls on everything else. That's the basic idea behind Newton's law of universal gravitation and Einstein's general relativity. But negative mass would flip that idea on its head. If positive mass attracts everything and negative mass repels everything, including itself, then we're dealing with a system of forces that's more complex and counterintuitive than anything we've ever observed in the universe. Think about what happens when you put positive and negative mass side by side. According to the math, the positive mass would be attracted to the negative mass, just like how normal gravity works. But, and here's the weird part, the negative mass wouldn't just sit there and be attracted back. It would accelerate in the opposite direction. Not because it wants to escape, but because that's how negative mass responds to force. So you'd end up with a system where both masses start moving, and never stop, creating a kind of runaway motion. Physicists call this self-accelerating pairs. It's a completely bizarre concept. Two objects chasing each other endlessly through space, one always running, the other always following, like an infinite cosmic loop that violates our understanding of energy conservation. But again, the equations work. The math says this is possible. And if nature found a way to make negative mass stable, this could be happening out there, right now, in regions we haven't even begun to explore. Now let's take this further. Negative mass might not just be something floating out in space, it might actually be space. Or at least, it might be a hidden layer within it. One idea is that the vacuum of space isn't empty at all, but is filled with what's called a quantum field, a sort of background energy that permeates everything. Some scientists believe this field might have regions where its energy density goes below zero. That's right, negative energy. It sounds like a contradiction, but quantum physics allows it. In fact, this idea connects directly to something called the Casimir effect, a real, observed phenomenon where two uncharged metal plates in a vacuum attract each other due to quantum fluctuations. That effect is one of the few pieces of experimental evidence we have that suggests empty space has structure, and that it can be manipulated. Now imagine amplifying that effect. Imagine entire pockets of space where these quantum fields are warped into regions of negative energy density. Those could act exactly like regions of negative mass. They might even be negative mass. And if that's true, it could explain one of the biggest mysteries in all of physics, dark energy. Right now, the universe is expanding, not just expanding, but accelerating. That means galaxies are moving away from each other faster and faster, like they're being pushed apart by some invisible force. This completely defies gravity, which should be slowing everything down. So, what's doing the pushing? Scientists call it dark energy, but the truth is, we have no idea what it is. It's just a name, a placeholder for the unknown. But what if dark energy is negative mass? Or more precisely, what if it's caused by a sea of negative mass particles spread out across the cosmos, gently repelling everything around them? That would mean we're not just living in a universe filled with mysterious dark energy. We're living in a universe that has a built-in repulsive force, a kind of anti-gravity woven into its very fabric. It would mean space itself is active, dynamic, and capable of pushing galaxies apart. This would not only explain the acceleration of the universe, it would also give us a new way to think about the beginning of everything. Because if negative mass is real, and if it has always existed alongside positive mass, then maybe the Big Bang wasn't a single explosion out of nothing, maybe it was a separation. A splitting of opposites. Positive and negative mass flinging away from each other at unimaginable speeds, creating a universe with structure, contrast, and motion built into it from the very first moment. And that opens the door to even more wild ideas. Like wormholes. Or warp drives. Or time travel. Because here's the thing. The equations that describe these science fiction concepts aren't actually fiction. They exist in real physics. The Einstein-Rosen bridge, the theoretical wormhole, requires negative energy to stay open. The Alcubierre warp drive, a faster-than-light propulsion system, also requires negative mass or energy to create a bubble of space that moves faster than light. And the only thing keeping us from building those things is the fact that we've never found negative mass. But if it's out there, if it's real, then all of that changes. Suddenly, traveling between stars isn't just a dream. Suddenly, manipulating gravity isn't impossible. Suddenly, the universe is no longer limited by what we can touch, or see, or build. Suddenly, everything is on the table. And here's where things get really crazy. If negative mass is real, if it exists as a shadow counterpart to everything we know, then there could be entire galaxies made of it. Galaxies that repel normal matter. Galaxies we could never see because their light never reaches us, because the very fabric of space bends around them in ways we don't understand. They might not just be invisible, they might be fundamentally unreachable. It would be like trying to look at something through a mirror that bends light the wrong way. No matter how hard we try, we'd never get a glimpse. But they might still be there. Existing. Evolving. Following a completely different set of rules. Some physicists have even suggested the idea of a mirror universe, a parallel cosmos made entirely of negative mass. One that formed alongside ours, but interacts with it only through gravity. If that's true, then the gravitational anomalies we've been observing, the strange movements of galaxies, the unexplained forces on spacecraft, the discrepancies in cosmological models, might not be random. They might be the fingerprints of another universe, pressing against ours from the other side of reality. And then there's the question of black holes. What happens if negative mass falls into a black hole? Does it cancel out part of the black hole's mass? Does it reverse time inside the event horizon? Does it create an explosion? Or a bridge? Could that be the mechanism behind Hawking radiation, the slow evaporation of black holes over billions of years? Could negative mass be leaking out of black holes right now, spreading through the universe as an invisible echo of destruction? We don't know. And that's the point. This isn't just speculation for fun. These are questions that real physicists are trying to answer, with real math, real simulations, real experiments. The idea of negative mass isn't fringe anymore. It's not pseudoscience. It's a serious contender in the race to explain the biggest mysteries in the universe. And the deeper we dig, the more it starts to make sense. So next time you look up at the night sky and see the stars, remember that what you're not seeing might be even more important than what you are. That the darkness isn't empty. That it might be filled with something real. Something strange. Something we're only beginning to understand. The Casimir effect shows us that the vacuum isn't just a blank nothingness, it's a dynamic, seething ocean of virtual particles that pop in and out of existence. When two plates are brought extremely close together, they restrict the kinds of virtual particles that can exist between them. As a result, there's more quantum activity on the outside than in the gap, creating a pressure difference that pushes the plates together. That pressure? It's coming from the vacuum itself. That's what scientists believe could be a form of negative energy density, a glimpse into the kind of conditions that might also exist in naturally occurring negative mass regions in the cosmos. This means that what we call empty space might actually be the most active, structured, and mysterious thing in existence. And if certain regions of that space possess negative energy or negative mass, then they may act like invisible barriers or repelling zones throughout the universe. They could be shaping the motion of galaxies, influencing the direction of cosmic expansion, or even affecting the behavior of black holes and wormholes. Which brings us to one of the most jaw-dropping implications: wormholes. According to general relativity, wormholes, or Einstein-Rosen bridges, are possible. They're essentially tunnels in spacetime that connect two distant points in the universe. But there's a catch. To keep the throat of the wormhole open and traversable, it would require negative mass or negative energy to prevent it from collapsing under its own gravity. Without it, a wormhole pinches shut almost instantly after forming. In other words, negative mass isn't just a theoretical quirk, it might be the key to unlocking faster-than-light travel and interstellar exploration. Imagine that. The only thing stopping us from jumping from one side of the galaxy to another in seconds might not be technology, or even distance. It might be our lack of access to something we've never seen, negative mass. If we could generate or harness negative energy, we could, in theory, stabilize a wormhole. We wouldn't need to travel faster than light. We just need to bend spacetime so that the light speed barrier becomes irrelevant. This idea has captured the minds of physicists and science fiction writers for decades, but the math behind it is real. Kip Thorne, the Nobel Prize-winning physicist behind the science in Interstellar, worked on equations that describe exactly this scenario, and they all require negative mass to work. But how would we even begin to find these regions? If they don't emit light, don't reflect it, and repel matter, then how can we see or detect them? Well, one strategy scientists are considering is to look not for the negative mass itself, but for its effects. Imagine light from a distant star traveling across space. Normally, when it passes by a massive object like a galaxy, the gravity of that galaxy bends the light, a process called gravitational lensing. This is how we know dark matter exists, because we can see how it distorts the light from galaxies behind it. Now imagine a region of negative mass. It would cause the opposite effect. Instead of pulling light in, it would push it away. Instead of focusing light, it would diverge it. If astronomers were to detect such an odd pattern, where light curves in a way that suggests repulsion instead of attraction, it could be a smoking gun for negative mass. There are a few strange lensing observations already that don't fit neatly into our current models. Some gravitational anomalies have been detected in the universe that appear to distort light in unexpected ways. Some scientists have even proposed that these anomalies could be caused by negative mass halos, regions of repulsive matter that we've misinterpreted as weird distributions of dark matter. Speaking of dark matter, what if we've been wrong about it all along? Dark matter is one of the biggest unsolved mysteries in physics. We know it's out there because of how galaxies rotate. Without it, stars would fly apart instead of staying in their spiral patterns. But we've never seen dark matter. We've never detected it directly. Every experiment so far has come up empty. But what if we've misunderstood the problem? What if the extra gravitational effects we attribute to invisible positive matter are actually being caused by invisible negative matter, pushing on things instead of pulling? Some theories suggest that large-scale cosmic structures could be stabilized not by extra invisible mass, but by the presence of negative mass that balances and counteracts normal matter. If true, this would revolutionize astrophysics overnight. It would mean that galaxies aren't being held together by invisible glue, but are instead embedded in a sea of negative mass that creates a kind of repulsive pressure, a cosmic scaffolding that we've only begun to recognize. And if these regions are spread throughout the cosmos, then we've been living inside a universe that's not just expanding, it's expanding because of them. That brings us to the biggest mystery of all, dark energy. Around 1998, astronomers discovered that the expansion of the universe isn't slowing down like everyone expected, it's speeding up. Galaxies aren't just drifting apart, they're being driven apart, as if some invisible force is pushing them away from each other. This mysterious force was named dark energy, and it makes up roughly 68% of the entire energy content of the universe. Let that sink in. The force that dominates the entire universe is something we've never seen, touched, or understood. But some physicists believe that negative mass could be dark energy. Here's how the logic works. Negative mass creates repulsion. If enough of it exists in the vacuum of space, then it would naturally push galaxies apart, not because they're being pulled by anything, but because the vacuum between them is expanding. The more space you get, the more negative mass exists within it, and the more it pushes. It becomes a self-reinforcing cycle. Expansion creates more space, which contains more negative mass, which causes more expansion. Sound familiar? That's the same runaway behavior we talked about with self-accelerating pairs, just on a cosmic scale. In 2018, a physicist named Dr. Jamie Farnes from Oxford proposed a radical new model. What if the universe is filled with a fluid of negative mass? He ran simulations that showed this could reproduce the same gravitational effects we currently attribute to dark matter and dark energy. One fluid. One explanation. Two of the biggest mysteries in physics potentially solved in one go. Of course, the idea is controversial. It challenges decades of assumptions. It suggests that everything from galaxy formation to cosmic expansion might need to be rethought from the ground up. But the fact that such a model can reproduce our observations is incredible. It means the door is open. It means that negative mass, once dismissed as impossible, might not just be allowed by physics, but required. And if that's true, then we have to start asking deeper questions. What happens when negative mass and positive mass interact on massive scales? Could entire structures, cosmic voids, filaments, and walls, be defined not by matter, but by the absence of it? Could our observable universe be just one bubble in a much larger multiverse, with different regions defined by different types of mass? Could the boundary of our universe itself, the edge of space and time as we know it, be a kind of transition zone between positive and negative mass? And most haunting of all, could we, ourselves, be inside a region shaped and controlled by negative mass without even knowing it? Interstellar Asterisk was one of the first to formalize the concept using real equations, and what he found was astonishing. According to the models, if you could inject enough negative energy into a tunnel of warped spacetime, you could hold it open long enough for something, or someone, to pass through. This isn't some far-out magic trick or sci-fi mumbo-jumbo. It's a legitimate consequence of Einstein's field equations, once you start playing with the idea that negative mass or negative energy might actually exist in the universe. But this leads to a deeper question. If negative mass is real, why haven't we seen it? The truth is, maybe we have. It just doesn't look the way we expect it to. For instance, one of the biggest mysteries in cosmology right now is the acceleration of the universe. Since the 1990s, astronomers have known that galaxies aren't just moving apart, they're speeding up. This discovery completely blindsided scientists because gravity, as we understand it, should be slowing things down over time. Instead, something is pushing galaxies away from each other faster and faster. That something has been labeled dark energy. But here's the thing, we don't actually know what dark energy is. We just see its effects. It behaves like a repulsive force on the scale of the entire universe. And doesn't that sound a lot like what negative mass would do? Several physicists have proposed that negative mass, if it exists in large quantities, could be responsible for this accelerated expansion. In this view, space isn't just expanding on its own. It's being pushed apart by vast regions of negative mass, scattered like invisible mines throughout the cosmos. And because negative mass repels all other mass, it would naturally force galaxies to accelerate away from each other without any need for additional energy input. And that's not even the craziest part. Some researchers believe negative mass could actually cancel out positive mass. Think about that for a second. If you had a region of space where the positive and negative masses were exactly equal, the net gravitational effect would be zero. That would mean matter could float in place, completely unaffected by gravity. It's like building an anti-gravity zone using nothing but the fabric of space itself. Now apply that to something like a black hole. These are objects with so much mass crammed into such a small space that not even light can escape. But if negative mass existed near or inside a black hole, it could change everything. It might explain why we see jets of matter shooting out of the centers of galaxies, or why some black holes seem to evaporate faster than Hawking's theories predict. It might even suggest that black holes could lead somewhere, through a wormhole, perhaps, if negative mass was present to stabilize the passage. And there's more. Let's bring in the idea of exotic matter. This is a broad term for any kind of matter that doesn't behave the way normal matter does. Negative mass is one candidate, but there are others, like tachyons, particles that travel faster than light, or hypothetical fields that exist in higher dimensions. All of these ideas come together when we start looking at the bigger picture of the universe. There's a growing suspicion among physicists that what we see, stars, planets, galaxies, is only a tiny fraction of what's really out there. The rest could be made up of dark matter, dark energy, and yes, negative mass. These components don't interact with light, so we can't see them directly. But their influence is everywhere. The rotation curves of galaxies, the bending of light around invisible objects, the structure of the cosmic web, all of it suggests that something huge, something unseen, is shaping the universe from the shadows. So what if negative mass isn't just a theoretical curiosity? What if it's common? What if whole regions of the universe are made of it, invisible zones of repulsive matter that we can't detect with our eyes, but that are warping gravity, twisting space-time, and accelerating the expansion of everything? We may already be drifting near one of these zones right now. That's not just speculation. Some models suggest that if our galaxy is moving faster than expected, or if there are anomalies in the background radiation of the universe, it could be because we're near, or inside, a region of space that contains negative mass. It wouldn't be dangerous in the way we think, it wouldn't pull us apart. But it could be influencing everything, the path of light from distant stars, the shape of time itself, even the long-term fate of our universe. This brings us to one of the most chilling and mind-bending implications of all. If negative mass exists, and it's scattered throughout the universe, then over time it could cause something called the Big Rip. This is a theory about how the universe might end, not with a bang, and not with a freeze, but with a tear. The idea is that as the universe keeps accelerating, the repulsive force driving that acceleration, possibly caused by negative mass, grows stronger and stronger. Eventually, it starts to overcome all other forces. Galaxies fly apart. Then solar systems. Then planets. Then atoms. Then the very fabric of space-time itself. It would be the ultimate unraveling. And the only way to stop it? To understand negative mass. To study it, manipulate it, and maybe, just maybe, learn how to use it. Because if we can figure that out, we don't just open the door to new physics. We might unlock technologies we can barely imagine, warp drives, stable wormholes, artificial gravity, maybe even a way to reach other universes. But all of that depends on one thing, finding it. And that's the hard part. Because negative mass doesn't emit light. It doesn't reflect it. It doesn't absorb it. In every meaningful way, it's invisible to us. It might be surrounding us right now, and we'd never know. But its fingerprints are everywhere, in the motion of galaxies, in the structure of space-time, and in the equations that govern our universe. So the search continues. Physicists are building more sensitive detectors. Astronomers are studying the cosmic microwave background for tiny fluctuations that don't make sense. Theoretical scientists are running simulations, trying to see if including negative mass makes the universe more accurate, more real. And every step we take brings us closer to the truth. Because the universe isn't just big. It's strange. And negative mass might be the strangest thing it's hiding. Into such a small space that not even light can escape. But what happens if a black hole comes into contact with negative mass? This is where the physics gets mind-bending. If you throw positive mass into a black hole, it gets sucked in, increasing the black hole's size and gravity. But if you throw negative mass into a black hole, the math tells us something completely different happens. Instead of increasing in mass, the black hole could lose mass. It could shrink. In fact, a sustained input of negative mass could, in theory, cause a black hole to evaporate from the inside out, reversing the entire process of gravitational collapse. That has staggering implications. It means negative mass could be a natural regulator of black holes. Maybe it's part of why we don't see certain theoretical black holes, like primordial black holes from the early universe. Maybe they never grew large enough because negative mass wiped them out before they had a chance. But there's another idea that pushes the boundary even further. Some scientists believe negative mass might not just exist in isolated clumps. It could form entire clouds or fields spread across space. These clouds wouldn't be visible in any wavelength of light, but they would have real, measurable effects, bending light around them, pushing matter away, creating gravitational anomalies. Astronomers have already found parts of the universe where galaxies seem to be accelerating in strange directions, where light curves more than expected, or where massive objects don't behave the way they should. These have been attributed to dark matter, or dark energy. But maybe, just maybe, they're actually signs of negative mass fields at work. And the most bizarre part? Negative mass could be stable. Once created, it wouldn't decay or transform like regular matter. That's because it would sit at the lowest possible energy state. It would be what physicists call a true vacuum. In other words, the universe might actually be designed to favor the existence of negative mass in certain hidden regions. We're just not looking at it the right way. Now let's talk propulsion. Negative mass doesn't just help stabilize wormholes. It could also revolutionize how we move through space. There's a concept called the Alcubierre drive, first proposed by physicist Miguel Alcubierre in 1994. It's a theoretical model of a warp drive, the kind of thing you see in science fiction, that doesn't violate the laws of physics. Instead of accelerating a ship through space faster than light, it contracts space in front of the ship and expands it behind the ship. The ship itself sits in a bubble of flat spacetime and effectively rides the wave. Sounds great, right? The problem? You guessed it, it requires negative energy. Without negative mass or negative energy, you can't warp space in this way. But if we ever found a way to generate or harness negative mass, it would suddenly make the Alcubierre drive not just possible, but practical. Interstellar travel could be within reach, not in centuries, but maybe in decades. Let's break that down a bit further. The ship doesn't actually move through space. Space itself moves around the ship. And because the ship isn't accelerating in the traditional sense, it avoids the time dilation and energy problems associated with near-light speed travel. You could travel 10 light years and experience only weeks or days aboard the ship. That's the dream. That's the game changer. And it all comes back to negative mass. But here's the kicker, negative mass doesn't just violate your expectations. It violates your instincts. In normal physics, when you apply a force to something, it accelerates in the direction of the force. Push a ball, and it rolls away. But with negative mass? It accelerates toward you when you push it. It reacts in the opposite direction. That's because Newton's second law, F equals ma, still applies, but if m is negative, the acceleration flips. This leads to some wild theoretical behavior. For instance, a negative mass particle placed near a positive mass particle would cause both to accelerate in the same direction, perpetually. This is called a runaway motion, and in theory, it could create a system that moves forever without any energy input. Sounds like perpetual motion, right? But it's not breaking any physical laws. It's just obeying the math of negative mass. Of course, we haven't built anything like this. We haven't found a pocket of negative mass floating in a lab. But we're getting closer to understanding how such a thing might be created. In 2017, a team at Washington State University created a fluid with properties that mimic negative mass, a so-called superfluid, made of rubidium atoms cooled to near absolute zero. When disturbed, the fluid moved in the opposite direction of the applied force, just like negative mass would. It's not truly negative mass, but it shows us that this kind of physics isn't entirely beyond our reach. We're learning how to simulate and eventually harness it. That's where things start to get philosophical. If negative mass is real, and it shapes our universe in hidden ways, what else don't we know? Could there be life forms made of negative matter, completely invisible to us, living in regions of the universe we can't access? Could entire galaxies or civilizations be hiding in the negative sector of the cosmos, operating under physical laws that make no sense to us? Could we one day create negative mass in a lab and accidentally punch a hole through space-time? The implications are endless. Even time travel, yes, time travel, becomes theoretically more possible with negative energy. According to general relativity, closed time-like curves, CTCs, are possible if you can bend spacetime in the right way. But to do it safely, without creating singularities or catastrophic collapses, you need exotic matter, specifically, negative energy. With enough of it, you could potentially build a time machine that lets you move backward in time without destroying causality. Again, the math works, the engineering doesn't. At least, not yet. So here's where we're left. Negative mass might be the missing piece of the universe. It could explain dark energy. It could revolutionize space travel. It could offer us wormholes, warp drives, even time machines. And yet, we haven't found it. Or maybe we have, and we just didn't know what we were looking at. The vacuum of space may be filled with it. Black holes may interact with it. Galaxies may be shaped by it. But because it doesn't shine, it doesn't reflect, and it doesn't absorb light the way normal matter does, it remains in the shadows, hiding in plain sight. And if we ever find a way to truly see it, touch it, and control it, it could change everything. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.